Becton Dickinson, and Treasurer of India, INCOSE India chapter, on behalf of the organizing committee, extend a very warm welcome to all of you for the second day of International Symposium on Artificial Intelligence, Machine Learning in Safety Critical Systems. Thank you very much all for joining with us yesterday and making the first day of summit successful for over 300 active participants. We hope you had a great learning experience and enjoyed the stall interactions, and we hope that you will have the similar experience today as well. Let us commence with the request to Director, Blue Sky Solutions and President INCOSE India, Mr. Mudit Mittal, to help us with a quick recap of yesterday's session and share today's agenda. Over to you, sir.
Yeah, thank you, Ankita. I hope you all can see my screen. All right. So yeah, so
sorry to interrupt, Mudit sir. Please could you swap into the presentation mode?
My bad. Is this better?
Yes, yeah. Thank you very much.
Okay, thank you. Thank you, everyone. So thank you, Ankita. Good evening, everyone. My name is Mudit. So we had a really great day yesterday, and we learned about so many new upcoming technologies about AI in safety critical systems. I'll take these few minutes to quickly introduce about the INCOSE India chapter and where we are headed and how can you all be a part of this. Okay, so just starting with INCOSE, the introduction to INCOSE Central. So some of these numbers might not be current, but we have more than 18,000 members. And yesterday we had great introduction by Ms. Lenny. So over here, we have over 53 technical working groups, and we have over 74 plus chapters across 35 plus countries. And if we talk about INCOSE India chapter particularly, we are celebrating 11th year in formation. We are chartered as INCOSE India South chapter in 2010, and we have more than 185 individual members. So with individual members and with CAM members included, we are about 250-ish members that are currently active. And then we are also associated with the several academic institutions, students, and non-members as well. And I'm really proud to say that we have been winners of several awards in the past few years. So we won Silver Circle Award, the Gold Award, and we were recently also given the Outstanding Chapter Award for continued performance of our work. So I'm really, really happy about that. And I would also like to bring to your attention about 3 local technical working groups that are very, very active. So the first one being the Architecture Working Group. They are doing exemplary work. They have been very much included with the various ISO standards. And if you are interested in contributing, please do share your interest. The second group that I would like to talk about is MBSE Working Group. It's been only 2 years since its formation, but again has been very, very active and also has won an INCOSE award in the very first year of its formation. Again, there we are doing several activities, and we've also done a MBSE seminar about 6 months back, which I'll be going to talk about soon. And then third, we have a PHM working group, Prognostic Health Measurement Group. And over there, it's a tight community where people who are working in aerospace and looking at safety features and also looking at prognostics, they are coming together to learn with each other and define new features about it. So again, if you are interested in any of these, please do reach out to us. I will be sharing the contact details in the end of this presentation. Here, I would like to quickly present to you what is the vision of our chapter. So our vision of the chapter is closely aligned to the vision of INCOSE Central. We too believe in this, that there's a better world through a systems approach. And we want to be recognized as the epicenter of professional activity in the field of systems engineering. And over here is a small chart describing how INCOSE India can become a center to working with various stakeholders like the industry, the academia, and different professional bodies like this event today. And we believe strongly that through our work, we can outreach to various people, to various experts in system engineering community, whether they are national or international, and become a networking platform where everyone can learn from each other and solve problems together. Okay. If you are interested in knowing more about us, please do visit our Incosa India website. And over there, you can find about the latest events, the chapter news, there's library and resources, and also details about each working group. So I would really encourage you to visit that place, that website, and know more about us. And just a quick summary of the previous event that we did. It was a joint event between Incosa India chapter and AESI design division. It was the sort of a first collaborative MBSE summit that we did, and it was a great success. We had close to 270 registrations, and again, 2 half days full of enthusiasm, and maybe more than 15-20 speakers and panelists from around the globe. And I think the success of that gave us a huge morale boost to even do this summit that we are in this today. And one of the few activities that have really been very good is the Incosa India webinar series. We've done about 18 webinars so far, and we started this during the last year. And again, we have very international group of speakers. Please feel free to join and also visit the YouTube channel to learn more about it. And then finally, I would like to thank you all and again welcome you all to this great summit. We have 4 hours of exciting knowledge sharing sessions with great speakers. Thank you all. And now I'd like to just hand it over back to Ankita for the rest of it. Over to you, Ankita. Thank you.
Thank you, Mr. Mudit, for setting up the D2 context and sharing the Incosa information. This really opens up a lot of opportunities for our audience. Thank you. So before we begin with our sessions, if you wish to ask queries or comment, kindly post it in the chat box at the right corner of the auditorium. We would love to hear from you and take up your questions. We shall now begin with our first talk of this day 2. Today's keynote address will be delivered by Mr. George Romansky. Mr. George began as the Chief Scientist and Technical Advisor, FAA, for aircraft computer software in 2017. In his role, he works to develop rules, guidance, regulations, and technical standards to help industry and regulators maintain a safety framework for aircraft computer software and use of artificial intelligence. It is my pleasure to invite Mr. George for the keynote address. Over to you, sir. Sir, please could you unmute your mic?
Can you hear my mic now?
Yes, sir. Thank you.
And are you seeing my screen or not?
Not yet.
Not yet. It's coming up.
Yeah.
Yeah, we can see it now.
Okay.
Yes.
Great. Thank you. So, artificial intelligence and machine learning is a fascinating topic, and within the FAA, we straddle a large range of types of a lot of aircraft, and we have different regulations that govern the way we work. And we have Part 25 for general aviations. These are small aircraft, 4 or 5 people, maybe 2 people. We have Part 25, which are the general transport aircraft that you know. Then we have the rotorcraft, which are the bigger ones, helicopters and smaller helicopters. But now we see a blend of aircraft coming up very quickly. And we have to categorize these as, these air taxis or UAMs, as we call them, where they have a combination of vertical lift, they go up and down, they fly horizontally, and they transition between those modes. So they are quite different vehicles and quite different control modes. We have the unmanned air system, or the aircraft. Currently, they're not covered by what we call type certificates, but that's coming up very quickly. The way we're organizing it now, we'll have type certificates for the smaller aircraft, but the other systems, which are the ground control segment, the communications, GPS, we call those associated elements. So in the past, people thought that we would combine all of these as part of a complete system. Well, the direction we're going is that that's not what will happen. We will have type certificates for the flying aircraft, and associated elements will be separate. For those UAS, the small ones, we have some new regulations we call durability and reliability, but these are intended for the small, low-risk type systems where we focus much more on system testing. We don't actually look inside the aircraft. The guiding principle of what we do, our regulations, is that the equipment, systems, and installations must be designed and installed to ensure they perform their intended functions under all operating conditions. And that includes safety. So a lot of these new type of vehicles, and some of the bigger ones as well, are introducing autonomy. When we step back, we see that autonomy, it makes it harder to ensure the performance. Autonomy kind of hides some of that behavior. What we find is that the operating conditions are much harder to quantify. When a vehicle flies and the sensor degrades, that causes us problems. You know, one example from the auto industry, we found that as the camera which looked outside the camera was inside, and when they changed the windscreen because of a crack, they found that the camera or the AI system could no longer recognize what it was seeing. Because of the optical properties of the glass, the camera lost its ability to recognize through its vision systems. So of course, we have to be very careful about sensor degradations. For example, the protective sheet over a camera, if that changes over time, then it might affect the AI, the recognition that the camera can perform. And then of course, we have systems or autonomous systems, and they blend with the operator. Now we have a combinations of the system and the operator. So this added complexity makes it much more difficult to constrain the interactions. Having said that, the rewards, if we can make autonomy successful, are very high. You know, right now we put people's lives in danger. Aerial firefighters fly over the flames and drop fire retardants. It'll be much better, much safer for pilots if they don't have to fly over these burning fires. So one of the key questions is, you know, what is AI used for? Right now, we use AI for various things, you know, for providing advice. Right now, people are working through the certification side for you know, a radio tuning. For example, if an aeroplane is flying along with some automation, now we have a co-pilot, which may be an automaton. As the aeroplane is flying and their traffic controller says, please retune your radio to 15.7, then the system retunes the radio to 15.7 automatically, because they can use voice recognition to work out what the instructions are. Right now, what would happen then is that the pilot, who would also hear the message, would have to press a button to confirm this. We don't trust the system to do the automatic switch, but we are looking at authorizing these radio tuning type devices. We have systems at the moment which haven't been fully authorized yet, but they do detect and avoid. So if an aeroplane is, or a UAS is flying in the air, it needs to detect intruder aircraft, birds, or perhaps helicopters or balloons. It needs to avoid those. We can use, or we do use AI for emergency. So right now we have a systems actually approved where if the plane is flying, a small, say 4 or 5 seater plane, and if the pilot has a heart attack and there is one of these emergency systems installed, then a passenger can press a big red button to say, I need an auto landing, please. And the system will find the nearest airport and land the aircraft and then switch the engine off, hopefully safely. Now, this hasn't been approved as a safety critical device. However, it's been approved as an emergency device because the alternative is possibly the loss of the aircraft. The other areas that we are seeing is the use of monitoring systems. So one very clever approach, which I thought was very clever, was to put in a camera behind the pilot. And this is an old aircraft that has the old type of instruments. And an AI system can monitor those instruments, extract information, and record it. So now we have a black box recorder without rewiring the aircraft through the use of AI. Now the question is, how accurate do these things have to be? How trustworthy do we have to be? And I'll try and explore these issues throughout the presentation. And one approach may be that if you have these, does it have to be better than a pilot, or can it be just as good as a pilot? So we'll explore this as we go along. As an introduction, there are many types of AI approaches, and I know that new ones are being invented all the time. We started off with rule-based and behavior trees, state machines over the years, and some of them have not flourished very well. What seems to be the most popular currently is the use of neural networks. I think that they're prominent due to the incredible computer resourcing that has become available. So through the use of huge computing capacity, these neural networks have become very popular. And we can break these down into unsupervised learning, where the system learns on its own. We have supervised learning, where we give it examples. We have reinforcement learning, where we have some heuristic reward function that extrapolates the information. I'll be describing these a little bit more detail later on. So the current approach to software, we have lots of experience with design and implementation. The guidelines, DO178C is well understood. But currently we have this prescriptive approach. So people know what to do and they check through and they say, have I done all of this? When we look at the verification, we can look at what the standards require and say, well, has this been done? It's not always that easy, but at least we understand what to do. But when it comes to certification of autonomy, it's hard. What we're finding is it's very hard to start scaling up. Some small systems are easier to certify. As soon as we start scaling up, it becomes difficult. We know that the data in neural networks is unstructured. And one of the things that we are struggling with at the moment is knowing when we have done enough. Have we tested it enough? Does the system behave as it's expected to? So the verification of the actual algorithm inside of the aircraft is fairly straightforward. Predominantly these architectures have very simple, very repetitive type nodes, and we can certify the actual code in an inference engine that's actually flying using DO178, and that's fairly straightforward. What we find is that very often a single data set or a very simple set of tests can explore all of the code in the neural network. But the data in the neural network is very hard to verify. There's no kind of direct correspondence between the direct behavior and what we can see inside, how we can make the observations. So what we're finding is that DO178 does not support the verifications of a neural network, an artificial neural network. So we need to change the strategy. We know that the traditional prescriptive strategies don't work. So one of the things that we're exploring is to build, say, a safety criteria through an assurance case. And in an assurance case, we are trying to develop compelling evidence that we believe that this system is safe. So we're trying to build in flexibility into this process, and we want to justify the process. So what we've been doing is researching this and developing an approach we call overarching properties. From the overarching properties point of view, it appears very easy. We have the stakeholder needs where we have a specification of the intended behavior. So we have the actual behavior, which is maybe at the system side, but now we have lots of stakeholders and they kind of know what the system is to do. But until this is documented, it doesn't count. So we're looking at the first property, which we call the intent property, is that we have a defined intended behavior. And this is now reviewed by some validation process where we have the customers, subject matter experts and users that can look at this defined intended behavior and say, yes, this is what the system is supposed to do. Our second property is correctness, where we say, is the system correct? Does it implement the defined intended behavior? And the third one is perhaps the most difficult, and we call that innocuity. Innocuity really means that, is there any behavior in the system that has safety implications? And we don't mind if there's additional behavior as long as it doesn't compromise safety. So these additional behaviors, as long as they are innocuous, in other words, they don't make the system unsafe, we can tolerate them. So now what we're looking for is a mechanism by which we can trust these three properties. And the overarching properties is a scheme where we allow people to develop an assurance case, a set of arguments that will reference out whatever evidence that the applicant has provided. And some of this could be DO178C type evidence. Some of it could be other evidence. But what we need is an assurance case that gives us a compelling reason to believe that the argument is sound. That's the direction that we are researching at the moment. It's still not done, but we have some experiments going on, and you'll see these coming up in due course. So how do we build trust? Well, we have an audit process, but the audit process is tough because all it's doing is taking snapshots. We have experience, or we can build up a service history. One of the things that we can do is we can build up through continuous training, where we have periodic updates. And as we do the periodic updates, we can do some validations against physical models. You know, and people like Tesla do this, where every day when you've driven your car, the system uploads the driving experience of the day up to the central computers, and the central computers take this data, but we know that that data cannot be labeled. There's just too much of it. So what they do is they compare the driving experience against models they have of how the system should behave, and we can build that up without retraining. Some people are talking of, well, let's build some monitors. We'll have an AI system. Well, if it doesn't work, well, let's put a monitor in there, and that monitor will verify that the system behaves within its parameters. Typically, the monitors are a simpler version. We'll come back to this. It's not so easy. Other people are proposing dissimilar implementations. So let's try 2 different or 3 different implementations, and the system can vote. That may work, but it comes with its complications. There is a lot of work being done in standards communities. I won't talk much about these, but there's a G34, which is a collaboration between SAE and EuroK. That's working on certification of AI. There is a document called UL 4600 for automotive and aviation. And there's a new group being formed to extend this. And we have research consortia under AVSI, and that again is looking to come up with the next extension to AFE 87. So when we start looking at these networks, we have we started off with very simple networks, and we've moved on to what we call deep neural networks. And what happens is that the learning process depends on some reward heuristic. If learning continues during the operational process, then we can continue to learn, but we do have problems. We don't know if the behavior is, as we go along, the behavior is uniform. Is the behavior under configuration control? For example, if the system is learning to drive a car and that experience is coming from Boston, well, we have the worst drivers in Boston. So is it learning bad habits by driving in the Boston environment? If the system continues to evolve, then how do we make sure we capture enough so we can do accident investigations? So the way we are leaning at the moment is that we want the system to be disabled once it's complete. However, it's disabled unless we need it. Because one of the things that we're looking at is putting system with lower criticality on the aircraft and have the user experience build up and then feed back in. So the system improves through user experience. But if the system improves, then we have to be very careful how it's changed and how it's optimized. So we do have problems. We think we need to do some level of learning, but we have to be very careful how this is controlled. As the system evolves, as the system is controlled, we have a number of questions that we need to ask. Does the system behave as expected? Can you explain what the system is doing? Are the explanations decomposable? So for example, we can use 2 networks, one to produce a map of the decision features, and the second one provides a confidence map of those features. So we have to balance between accuracy of the AI system, explainability, but a lot of this depends on context, and we are struggling to work out exactly how to do this. So we need this interpretability because we need confidence that the system works. We need to protect the system to make sure that it doesn't have a bias and it doesn't drift off into bad habits. Also, we need this interpretability so that we can help, so this helps the authorities to check against the regulations. If everything is a black box, then we struggle to be able to certify this. Some people are trying to bound the behavior. They say, oh, let's put safety in our nets around the non-deterministic parts of the system, and then we'll have multiple monitors. The trouble is, at that point, we are saying, well, we're going to trust the monitor. So if we have a control system and then a system which does the monitoring, we have to certify the monitor as well as the system that's doing the control. What if the monitor actually goes wrong? What if the monitor disengages the control system, which may be functioning correctly? So we have to be very careful with just monitoring. It's not so easy to be able to switch over the trust from the control to the monitor. And some people are trying to use this safety reinforcement learning by putting barriers around this, shielding the reward functions. That may be fine if you can put barriers around the control system, but sometimes the control goes beyond those barriers. You can't always just have be able to fly inside a constrained environment. Sometimes the environment changes. We may learn to fly in an environment, but then there's an emergency and a medical helicopter needs to fly through. The environment then changes. We need to cope with that. We do rely on a lot of data for training, especially the neural networks. They have huge amounts of data. Very often we extrapolate and we provide even more data. For example, one of the systems that we've been monitoring, where the applicant is using video cameras to work out where an airfield is, recognize the airfield. They extrapolate the data by saying, well, we'll take these images and we'll label those images so we can extract the airfield from the whole picture, but then they can digitally rotate the image and have an extra set of images, or they can digitally edit the video so that you can add in various levels of fog to extrapolate the data that they have. Trouble is that, if you have too much data, then you can't see the wood for the trees. We have a problem where we can start doing overtraining, where the system has learned from the data it's seen, but it hasn't learned how to extrapolate that behavior to data that it hasn't seen. So there are ways there's lots of work being done, lots of research being done on how to take this data and reduce the dimensionality, and people are trying to fuse the sorts of data that we have. Ideally, we want to have the data and say, well, this is what we have, this is what we need, and this is enough, and it's no more. If I look at some of the successes for AI, medical imaging has become quite successful in this field. And in some cases, it's for heart conditions, for lung conditions. Some people are claiming that their AI system is more accurate than the human counterparts. We have a fuel measurement system developed by BF Goodrich, for example, a while ago, where they used a model to do the training. And they found that the model, the resultant system was smaller, it was faster, it was more accurate. Unfortunately, we still don't have a way of certifying this and being able to trust it. We have a lot of research in the FAA, both flying systems and on the ground, things like flight power, flight plan contentions, airport type planning. We're looking at analysis of data using big data analytics, using data clustering to try and extract information out of the mass of information that we do have to try and show or to try and predict potential problems. When we look at what we actually need is we have what we call a safety continuum inside, the FAA, and we say, well, we have flight over low population areas, but we also need flight over highly populated areas. We have UASs, for example, with very low kinetic energy, therefore low risk, and we have high kinetic energy and high risk. And the same can be said for aircraft and aircraft systems. So we have this continuum of safety, and now the continuum has to look at, they said, well, if we have a low risk system that is expensive to certify so we don't deploy it, it may be that by not deploying it, we've added risk. So if we're not deploying a firefighter, then a human pilot has to fly over the fire. But if we say, well, it's too expensive, or it's expensive to certify to the full standard that we currently have, then we can say, well, can we lower the certification costs? Can we lower the what we're looking for? After all, we don't need a detect and avoid over a fire because there won't be a balloon or a small aircraft flying over there because there's a fire there. There won't be any birds there. So what we're looking for is to find a balance between the needs of certification, the cost of certification, and what we can achieve at the other end. And there's a balance, and we are striving for that to find and define that balance. We have some proposed uses, for example, for autonomous systems, where we have a co-pilot using speech recognition, for example. And initially, these are low risk, and we can, the system goes through and it's listening to the air traffic controller. And if the air traffic controller says, can you tune your frequency to 105.7, then the automated system will retune the radio automatically. However, initially, it does not complete that transaction. It's up to the pilot who's flying to say, I heard the same thing. It has retuned the radio so they can pull the button to engage that new radio frequency. So this is a way of gradually transitioning to a level of trust. We are looking at the plane landing type situations where we have worked on a research project with Dedelian's research, which they did for the FAA, where they looked using a convolutional neural network, using cameras, where they can look down and they can recognize and find a runway. They had some really promising results where as the plane was flying, there was an airfield and a river right next to it, a canal right next to the airfield, and there was a bridge across the canal. And the system looked at this, and from above, it looked like a wet runway. But the system was sophisticated enough that after a few images, it recognized this, well, it looks like a runway, but it's not a runway. And it then switched over and it found a real runway. But these are the types of systems we are looking at and learning how to trust. We are looking at sense and avoid because we need that. There are a number of systems being developed. None have been certified officially, but there are systems that are being used. A clear UAS landing, mainly for package delivery. You want to make sure that there's no moose or taxis or whatever, some vehicles on the runway before the plane lands. Following a pipeline, used quite successfully at the moment. We don't know how to certify it fully, but it's used quite successfully. And we have experiments where we have a center line following on a landing strip. What we're finding is its behavior is kind of we struggle at the moment when the sun is very low or the sun is either setting or climbing. The shadows kind of confuse us for the moment. Still a work in progress. So when we compare what we have is that, if we compare what the pilot does and a neural network, let's say with autonomy, we see that the pilot requires training, the pilot learns through experience, and that experience is ongoing, trusted by the public. However, we do have to retrain the pilots periodically. In a neural network, we're looking at a system where how much training do we need? How much training do we have to keep doing? Just like the pilot, do we have to continue training? There's a lot of parallels here. If we look inside the neurons and the connections, we don't understand what's going on inside a neural network, just as we don't understand inside a pilot's head what they're thinking. So we have a challenge currently. Do we have enough pilots for the future? There is a shortage of pilots now. That may get worse as we go along. And on the AI side, the current challenge is, how do we establish trust? So just 2 slides left. And what we're looking at is to say, well, how do we learn? Right now, our learning process uses very high computational resources. Very often, these training systems are in the cloud, and they have incredible computing resources with parallel computing and GPUs and special types of processors where they may do thousands of calculations per microsecond in parallel. And these systems are currently being used, but they're starting to be kind of like black boxes. We buy those services and they're becoming black boxes to us. So these frameworks are being offered, but these frameworks are then updated and they are extremely expensive. And now the question is, do I do the training on my own network, which might take a month or 2, or do I go and use this framework, which I buy the services, and I can reduce that training to an hour or 2, so I can try different things. But then if we use these frameworks, does the learning process evolve? Is it under control? So these are struggles for us. So in summary, we have seen some very successful deployments and some very successful uses of AI and ML, the machine learning. However, right now, we still don't know how to trust fully. We don't know how to trust AI and ML systems. And the bigger problem from my view is right now, we don't know what we don't know. So this is an ongoing process. We are learning, we are building up experience, and we are trying to build this experience up through low risk systems first. And as we build up, but our problem here is that the regulatory requirements for certification is struggling. As we normally say, well, hurry up and wait. We need it today, but we need to wait. Incredible progress is being made, and the FAA is desperately trying to promote innovation. We have a number of projects where we are helping automation, we are helping the use of AI, etc. But we have to temper that with the risk of introducing this type of technology. That concludes my presentation. Over to you.
Thank you, sir.
Do I stay on for questions or?
You have a question for you, George. Yes. Yoga here. I don't think we have questions from the audience yet. I just wanted to know what would be your guess, I guess, would be a timeline when we would be kind of ready to have some AI systems certified, which can be doing some automation with the passengers.
Depends. As soon as you said passengers, we haven't.
Yes.
So we have. So we have the small UASs, and we have a whole range of them. They go from, we do have systems at the moment, less than 10 pounds, less than 20 pounds. And we have some which have been isolated to fly from, let's say, from a clinic to somewhere else over a defined area, not flying over people. And these systems, we can trust, we can do those. But as we start going up, the next thing we're looking at is, well, let's start going up in size, maybe 100 pounds or 120 pounds package delivery. Well, again, package delivery over water, perhaps, that may be fine. And we have systems under development where the people are saying, well, we'll only use package delivery. So they use the concept of operation to say, well, will you approve this under these safety properties? And we can sort of look at it and say, yes, okay. But we know that as soon as we say, yes, it's okay to fly over water and there's no, there's only polar bears and penguins, that type of thing. But as soon as they have that, they'll say, we have a new concept of operation and we want to fly from the middle of Los Angeles over to deliver a package somewhere over the mountains. Now it becomes hard because now your concept of operation is different, even though you're trying to use the same evidence. I believe, my personal belief, when you look at the people doing the AAM, the air mobility, most of them have gone to using pilots as the first step. So they use pilots, they'll use their experience. There's still plenty of problems to solve with electric motors certification, with new composite materials being used. So they want to learn how the system flies using a pilot and then gradually build this up into partial use of automation and then full automation. I think full automation, my personal view, and again, this is not policy, my personal view, full automation is at least 5 years away, perhaps a lot more.
Yeah, thank you, George. I think we can take one more question, George. This is, are there any proposed DO guidelines specifically for AI/ML for airborne systems? This is from Amit Sharma from the audience.
There's no DO standards. There is the standards being developed for lower criticality levels. SC240 committee is being developed. The SAE is developing, the G34 committee is developing standards. But you see, the way it works is that the standards authorities develop the standards. And once the standards are there, the authorities look at this and the authorities say, yes, we'll accept your systems using this standard with the following conditions or with the following provisos. So it doesn't have to be a DO standard. There are other authorities, the ASTM, SAE, that are developing standards in this area. And it may be that they become the standard of choice. I don't know. It may be that we'll have to wait until there's a DO. I don't know. But initially, we can approve standards providing they are presented to the authorities. We look at it and say, yes, we can accept this with these constraints and these restrictions. To my knowledge, RTCA is not developing one of these standards yet. However, they might in the future, I don't know. So it's an exciting time. It's a challenge, but it's an exciting time.
Yeah, it is. Thanks, George. Thank you very much for sharing your valuable insights on the benefits and challenges using AI and the current approach and the ongoing work. It really helps. Thank you very much. Okay.
Thank you.
So we will now have our track keynote address by Dr. Barclay Brown. Dr. Brown is an engineering fellow at Raytheon Technologies focused on MBSE and artificial intelligence, machine learning, and systems engineering. He is certified expert systems engineering professional, ESEP, certified systems engineering quality manager, and CIO of Encose for 2021 to 2023. I'm extremely honored to invite Dr. Brown for the track keynote address. Over to you, sir.
Okay, just getting ready. There we go.
Yeah.
All right. Do you see my screen and my camera and everything?
Yes.
Okay. All right. Good.
Okay.
So, hi everybody. And what we're going to do today in this, and it's kind of perfect, you know, following George here because he laid out a lot of the problems. And here I'm kind of going into some, I would say, some concepts that will be parts of the solutions of how we deal with this. This isn't the full solution, right? But one of my kind of passions is trying to communicate concepts in the AI space so that everyone can understand them, right? Even people that don't have, you know, a background in coding and math and that sort of thing. And so there's kind of two ways you can listen to this. If you already know all of this, maybe this will give you some new ways to explain it and to talk to people who don't understand it. And if you don't know some of this, then maybe some of this will be new. So let's jump right in here. So let's see, here we go. So what we're going to look at is the role of data in these AI ML applications from a systems perspective. How should systems engineers think about data? That's it. Oh, okay. I'm sorry. I'm seeing another video shared there with the echo of the screens. How much, and then this kind of central question, how much do systems engineers really need to know about AI ML, right? And that's a tough question, right? Do we need to train them all to be AI ML developers, to be able to build neural networks and things like that? Or do they not need to know anything? They just need to watch the Terminator movies and they know all they need to know about AI, right? And of course, the general public, that's their picture of AI, right? Is that, okay, what we see in the movies and so on. And specifically in data, can we just leave data selection to the data scientists? The systems engineers don't need to worry about it. Okay, so here's a quick quiz. And you don't have to put the answers in your chat, but just think about this. So training data in an AI ML application is most similar to what in traditional software development? Okay, is it most similar to test data? You know, in traditional software, we have test data, right? Configuration settings or compiled object code or source code. And we could add another choice. I added it in some versions, or a database. Is it most similar to a database? You know, we're talking about the training data for AI ML. And what I'm going to suggest, perhaps surprisingly, is that the training data in AI ML applications is most similar to source code in a traditional application. Okay, so it is actually the data, the training data, that determines the performance of the system. And of course, it goes through a neural network. And as George pointed out, it's not, you can't necessarily trace it and say, okay, here's this bit of training data, and then here are the weights and biases in the neurons, and then here is the performance of the system. But that is what determines it. In other words, many of the problems I'm going to illustrate here in systems have to do with the training data and with problems with the training data, and how that is a systems engineering concern, not just a data science concern or a ML developer concern. So here, let's start with one sort of statement that gets thrown around. Well, AIs are dangerous because they get things wrong for unknown reasons. You know, they perform, and sometimes they do well, and sometimes they get it wrong, and we don't know why, right? People think that way. Well, let's take my favorite little story here about the green school bus. So this example is an application. Let's say we're doing an image recognition application, as George mentioned, also like a convolutional neural network or something like that, to recognize images from cameras or video or something, right? And we're going to deploy it on a battlefield, right? And it's going to recognize different kinds of vehicles in a wartime situation, let's say, right? And so how do we train it? Well, we give it training label data, images of, you know, tanks and military trucks here, and a few different kinds, and a school bus here, because we do, and then some civilian vehicles, you know, Jeeps and SUVs and cars, and, you know, all kinds of things like that. We give it all of this data and we train it. And of course, as you know, right, we train it and we test it, and we find that it ends up performing really well. on all the vehicles. We segment the data, how you do in training and test and validation sets, and we test it and so forth. And we find it's not overfitting, it's doing well. The confusion matrix shows the false positives and the false negatives, all looks good, right? And so we say, we're ready. We're going to deploy this system in the field, and we put it out there. And then one day into the environment rolls a green school bus from the Greenville High School. The Fighting Toads is their team, of course. So naturally they have a green school bus. And so this green school bus rolls in. And so the question is, how is the system likely to identify this green school bus? And I suspect, and one day I'm going to do this, right? This is just a story, but one day I'm going to try this out in reality, that it is not going to recognize it as a school bus. It is more likely going to recognize it as a military truck. And that's because the only school buses in our training set were yellow school buses. And now I don't know, what color are school buses in India? Are they yellow? I don't know. We mostly they're yellow in the US, but there's other colors, right? So if we have made the mistake, I'll say, of putting only yellow school buses in the training data, then we can't blame the AI for not recognizing a green school bus, right? Because you can think of the AI, if you want to anthropomorphize it, which you should not anthropomorphize AI systems because they hate that. They really do. So there you go. We didn't think it's very literal. If I train it only on yellow school buses, it's going to learn that color is essential to it being a school bus. And therefore it is very unlikely to recognize something that's not yellow as a school bus, right? So we have misled the system. We have mistrained it. This is not the AI's fault. This is not even the developer of the convolutional neural network. It's not their fault. The fault is the training data that we have selected for this. So the school bus can be identified as a whole bunch of different things, right? But very likely it's going to be recognized. And you would let's take a look at these choices here. Choice E, the system says, well, it's sort of like a school bus, but it's a color I've never seen before. Now that's the answer you'd really like it to give, wouldn't you? Right? But that's very difficult. And our neural networks don't think like that, not in the current technology, right? That would be neat if it could do that, right? And it's not going to pick F, because if you know how neural networks are done, they pick the most likely thing of a number of choices. And sometimes you get a certainty, you can show the certainty level. So you might, it could actually give roll F if it said, well, I'm not over, I don't know, 70% certain that it's any of the categories I know. And then it would say, I don't recognize it, because I'm not certain enough in my best choice. But very likely, since it's a vehicle, it's got four wheels and it's green, it's going to look like a military truck, I suspect. All right. So here's the nightmare headline, right? Autonomous vehicle identification system based on the latest AI technology misidentifies school bus as enemy troop transport. Can you imagine the headlines in the paper, right? And then who is at fault? Well, someone else, not me, of course, right? Or the systems engineer or the data scientist or the developer or the tester. I think it's the systems engineer, because the systems engineer is the one who has to be familiar with the whole application, the parameters of the application, what kind of vehicles could be expected in the environment, and to provide training data or to require training data as a requirement, right? To cover all of that. All right, so I'll give you one more little exercise, and then we're going to show you some concepts of data requirements, which is, I think, a new kind of systems engineering discipline that we're going to have to embrace. We don't have time to go through this exercise, but if you came to an earlier session earlier this year at the INCOSE conference, we did this at length, and it works like this. We show what the intent is to give you a kind of an intuition for how neural networks learn to recognize images in this case. So we're going to have you be the neural network, okay? And it works like this. So first of all, we're going to show you labeled data. So these are labeled images of trees, of types of trees, okay? So there's an elm tree and there's a maple tree we show you. And this is labeled data, right? A pine tree, and you should be learning. Are you learning now about these trees right here? Here's an oak tree, okay? And then here is okay, now we test you, right? So what is this? And you're probably going to say, oh, that's what was it, a maple tree? I forget now, because it's the exact image you saw. So that's easy, right? You're saying, I test you on the exact images that I first trained you on. And that is the first kind of testing we do in a network. So we test you, do you get this? But now here is an image that you haven't seen, but it's the same kind of tree. So then you have to generalize a little more. Did you learn enough about pine trees in this case to say these are pine trees? Even though I haven't seen this image, I get pine tree, right? And you test it that way, right? And so we give you some other images to test and so forth. So the whole set looks like this. Here's the training set. Here's the development set, which is for training evaluation, which contain, I believe, just images from the same training set. And then here's a test set that are images that have not been seen in the training, right? And so we test on that, and then we have the answers for the test set so we can evaluate. So if you think about a human doing this exercise, making multiple passes, right? We don't give you just one pass. We'll go through these 20 or 40 images of trees multiple times. So you can see them again and again. And each time you are thinking, well, what am I learning here? I can't memorize the image, but I have to learn something about the color of the tree, the shape, the leaves, and you start to figure out these features that allow you to identify the tree. And at least theoretically, that's what the convolutional neural network is doing, is picking out these features and then trying to generalize. So the idea is once we understand this, we see why different variations of the data are so important, right? Okay, let's go on. Now, another story here about data and bias. So we talk a lot about bias in AI systems and how it's scary and awful and so forth. So I want to give you an example. The question is, the purpose here is to show the difference between bias in the world and bias in the data. So in the world today, and I think this is worldwide, not just US, in 93% of nurses are female. 93%, that's the fact, right? 7% are male. And that's not good or bad. That is simply the facts today, right? That's how it is. You can have another conversation about, should it be that way? Well, maybe there should be more men in nursing, but that's a whole different conversation. Right now, today, this is the split that exists. So if we pick we're doing an application here to try to recognize nurses by photos, let's say from a video camera in a hospital. So we need to know where all the nurses are. And we're going to do this with a video cameras in the hallways, let's say. So a real world data set would contain 93% female nurse photos and 7% male nurse photos. And that split would match the real world. So isn't that the right way to do it? Well, the problem is if you train the system that way, and in this right here with a 93% female and 7% male, the system is likely to perform very poorly recognizing male nurses. And that's because it hasn't had enough training experience. It only got 7% of the training was male nurses. So a better training data set would probably be 50% male and 50% female nurses, even though that's not the mix in the real world. But that will probably produce a better performing system. Now let's extend this example just one more step, and this is really fun. Let's say we're going to not just recognize nurses, but we want to recognize doctors also. All right. Now, in the world, doctors are 50% female, 50% male. They're very nearly half and half, evenly split. So that's the facts again. So we would have our data set be 50% female doctors and 50% male doctors. Okay, that seems logical. That's pretty obvious, right? But now let's say we do this combined system. So here's the training data. This whole thing down here is the mix of the training data. So, and we'll do the 93%, 7% in nurses and 50-50 in the doctors. Now what happens? Well, if you think about the conditional probabilities and the likelihood here, I'll just kind of make the bottom line. Is it quite possible that this system, because it's been so heavily trained on female nurses more than female doctors, and so heavily trained on male doctors versus male nurses, that it's going to make some mistakes? And think about the kind of mistakes it's going to make. All right. I suspect it's going to misclassify a number of female doctors. It's going to classify them as nurses because of the way it's been trained. And it's going to classify a bunch of male nurses as doctors. Isn't that shocking? Now, can you imagine the headlines that are going to come out of that? Because this is looks like pure sexist bias, right? But all it was a bad choice in the mix of the training data, right? Because of the real world splits and so forth. The idea is we want to remove those kinds of biases from our training data. In other words, there's nothing inherently female about being a nurse. So therefore, gender shouldn't affect nurseness, right? Because you can have a male nurse, you can have a female nurse. They're not, it's not essential to being a nurse, the gender. All right. So to finish up here, a data requirements approach. So how would we specify data requirements? If we say, okay, systems engineers love to specify requirements, how do we specify data requirements for an AI system? And we'll say, these are not your dad's requirements. You know, these aren't the kind of requirements your father and your grandfather and grandmother did when they were systems engineers, right? So DADS is the acronym here. Okay, so let's look at each of these. So the first one is diversity of data. So the AI doesn't generalize like we do. Small children, we notice, only have to see a couple of dogs and they can recognize all dogs. Now, we do not know how they do that. If we did, we could maybe program neural networks to do that, but we don't. So that would be wonderful. And we try, right? But the AIs are much more literal. So what you would like is every kind of size, type, and color of dog out there, right? Every breed, every size, and so forth. That would be great. That would be the best way, right? We've got to understand what's expected in the environment. So again, that's a systems question, and it's the systems engineers that have to specify this diversity of data. Okay, the A in DADS is augmentation of data. So augmented data is a software generated variations of training data. So we can take one image that you see right here and vary it in a bunch of different ways through software. This is automatic, right? Varying the colors, varying the angle, varying the orientation, the tilt, the rotation, all those kinds of things. And you can do quite a lot of interesting stuff this way. And this is so common that it's built into some of the AI ML systems. You just tell it, I want to vary each image, and it doesn't even have to store all the variations. It just generates them and uses them. So if we generate all these augmented images and then use those to train the system, it will perform better. So systems engineers should be concerned with specifying what variations should be included. So for example, a dog is often seen in different angles. They can roll on their back, they can be jumping, they can be standing and so forth. But a horse is less likely to be upside down, and things like that. So the systems engineer knows what's going on. Vehicles tend to have their wheels down, right? We don't probably need to train the system on vehicles with their wheels up or something like that, Okay, D, the next D is distribution of data. So distribution has to do with the number of each kind of data. That was the nurse problem, right? How much of each class of data do we train the system? And so we have to think about that in the ways we've already outlined. So that's distribution. That's a separate consideration for requirements. And then the S is synthesis of new data. To me, this is a fascinating area. This is where the computer actually synthesizes, actually creates training data on its own. And a fellow named Lawrence Moroney, I put the link down there, he's a great AI teacher and researcher, created a data set he calls Horses and Humans. And it simply is computer-generated images of horses and humans that he generated using sort of game CGI kind of software, how computers can do this. And he generated a whole bunch of horses and humans, and then he trained a neural network using that synthesized data and then tested it on real photos of real horses and real humans. And the system performed very well. And to me, this was a really interesting finding, right? That you could train a system completely on synthesized data and it would perform well on real data. I was kind of surprised. I don't know that I would have predicted that would have worked, right? So that's a fascinating area. So can we figure out ways to synthesize training data that will help our neural networks perform better? So you could think of this as a training data life cycle, much like the software or the system goes through a life cycle, so does the data. Some analysis, some design, some implementing the data, finding the data, synthesizing the data and all this, and then maintaining it, enhancing it over time, gathering new data, and so forth. So that's the idea. Okay, so just to wrap up here, the key takeaways are that systems engineers have to be aware of this role of training data and how to write the right requirements for the training data and be involved in that. And that the key areas are diversity of data, augmentation, distribution, and synthesis, synthetic data. So I will stop there, see if there are any questions. Let's see, are those questions in the chat that I should consider, or maybe those are for George?
Yes, I don't think we have any questions.
No questions? All right.
Thank you very much, Dr. Brown, for sharing your valuable insights and also the interesting green school bus problem. I think we would love to hear the outcome of your experiment, and thanks for introducing the DATS concept. Thank you. Okay, so thank you audience for your queries, and I would also like to thank all the speakers for helping to address the queries by chat as well. We now move further to the next talk by Mr. Ritesh Ghimire. Mr. Ritesh has been actively supporting the FAA, US industry, ANSI, NASA, and leading the outreach of the ANSI US standardization roadmap to support the FAA's global leadership. He's the custodian of ANSI US standardization roadmap. He has been actively supporting development of industry standards needed for type certification of US. It is an honor to have you with us today, sir. Please may I request you to share your insights with the audience. Over to you, sir.
Thank you. Audio check. Can you hear me well?
Yes.
Okay. Thank you so much. Yeah, we are really honored to, get this kind of invitation, especially from yoga, all of you, as well as the Aeronautical Society of India, IEEE India, and finally the INCOSE India chapters. So I am actually representing the work of 400 plus people. Okay, let me just a second. Let me share my screen really quick. And I may need, okay, while I'm talking, can you see my screen now?
Yes, sir. Your screen is visible. So may I also request you to turn on your camera, I guess? Yeah.
Oh, yeah, I'm having some issues on my IT issues on my camera. I apologize.
No worries. Thank you, sir.
Yeah, thank you. So yeah, we are really honored, and I'm actually presenting the work of 400, 400 plus people, individuals coming from 250 organizations or companies to, kindly mention about the artificial intelligence section that we, with the help of industry and this large group of people in this team installed in 2018. So first of all, okay, sorry. Okay, first of all, I would like to appreciate the great leadership of Jim McCarvey. He's the Senior Director for Standards Facilitation at ANSI, and obviously the American National Standards Institute, the ANSI, for facilitation, development, and maintenance of the ANSI UAS standardization collaborative roadmaps. And obviously ANSI has other roadmaps also. And one of the other roadmaps, I think, is dealing with AI in healthcare or something like that. So I kind of want to acknowledge, Jim and the great support and leadership of ANSI. So let's go to the next slide. So here, this slide just shows that, and it, what it depicts is that the contribution and this ANSI roadmap collaborating work is considered an individual contribution. I mean, even though we use our, employer times, all that, but first of all, we, represent as a technical or subject matter expert, to work together at an enterprise level to really, promote the industry and growth in a safer and secure manner. So this is just the one page of 412 page long ANSI US roadmap version 2. The left column, I think I briefly mentioned, it's a huge enterprise level teamwork, and collaboration, standardization, road mapping are the key components here. And we may ask, what exactly is the standardization collaborative in ANSI, right? So the standardization collaborative is a mechanism to advance cross-sector coordination in the development and compatibility of standards and conformance programs needed to support emerging technologies, as well as national and international priorities. And obviously, this is very pertinent to this meeting. And on the far right side, we have the mission of ANSI UASSC. Obviously, UASSC stands for UAS Standardization Collaborative. And its mission is to, insert and suite, Its mission is to support rapid development of needed industry standards for certification of UAS. And while this roadmap is meant for UAS unmanned aircraft systems or RPAS, remotely piloted aircraft systems, urban air mobility, advanced air mobility, the technologies are common. And obviously the AI ML that is listed in section 6.11 of this roadmap, as well as software, system safety, specifically the technologies, we are listing a lot of common technologies that are also applicable to traditional aircraft certification and aviation. And so the achievements that we have accomplished so far, this team, is we published version 1 in 2018, 2 in 2020, and we published first the GAPS progress report in 2021, June. And it has thousands of standards, regulations referenced. And this version 2 roadmap has 71 open gaps with associated list of recommendations. And open gaps here mean that there are no industry standards that adequately address the specific topic or problem statement for type certification, so compliance purposes, to be used as a means of compliance or MOC. So this, I believe this, this chapter 6, right? It has a bunch of sections and subsections. I think this is very pertinent to, basically all of you, because most of you, work on, certification work, as Yoga mentioned to me earlier. And so this chapter 6 is tailored to really support the people doing the certification work, both from the regulatory side, government side, as well as the industry side, and as well as our, the designee communities like the DERs or ODAs as organizations, right? So, and obviously we all know, like, the hottest potato on the hottest plate is the detect and avoid technologies, right? We call DAA, for the RTCA subcommittee SC228. And obviously, subcommittee 228 is developing standards and solutions for DAA, C2, navigation systems, among others. And then we have ASTM F38 that is also developing solutions for DAA for lower end UAS. So now let's focus towards the bottom of this page here, section 6.11. The title is Enterprise Operations, using level of automation, autonomy, and artificial intelligence. The team chose the word enterprise operation here to signify that this is really, even though the roadmap is for UAS, right? But when we really talk about the artificial intelligence, right? We are really talking about the systems engineering, and it is a teamwork. So, and again, everything is almost like, how do I say, not really inseparable, almost like an inseparable situation, right? So we really need to know the basics of avionics, right? We really need to know the airborne software certification requirements. And obviously we need to also, integrate this detect and avoid technologies, other collision avoid systems, CAS, that we have, a number of standards from RTCA subcommittees and others. And obviously we also need to address the recorder systems, right? The black boxes. So anyway, so these are just some of the different, subtopical areas or technological areas. So that's what we are really talking about in section 6.11, when we really mention here about enterprise operations using different level of automation, autonomy, and artificial intelligence. So let's go to the next one here. So this slide is basically copy and paste from the ANSI map. And I obviously put, I think 5-star, right? Star, 5-star, just to, remove the, non-generic information. And this slide kind of shows like, this is from the introductory part of this AI section from the roadmap. And obviously we all know one of the most challenging issues in all aviation, right? Manned, unmanned, or hybrid aviation, is the incorporation of fully autonomous flights of an enterprise or fleet of aircraft or unmanned aircraft or in between aircraft within the scope of airworthiness approvals, such as specifically focusing on the type certificate or supplemental type certificate or amended type certificate and other certificate, right? So that's why like this section, when we collaborated and when we received great support from Boeing, Lockheed, Northrop Grumman, and among others in 2018, we really created this section to really enable the future and then current works to support the type certification of any aircraft, right? And the second point here is the there are a lot of important factors that we need to consider, right? The first is the observability, predictability, and intervention when required are the main factors in trusting and accepting fully autonomous flight. And I think it kind of like echoes, sort of, tags along with what George and Barclay had mentioned this morning. And obviously there is a lack of consensus. And when we talk about consensus here, we are really talking about industry consensus standards from industry groups on a certification process. And obviously, the second highlight of second bullet point here is that we also need to really learn and do a lot of dry run and gain a lot of experience through the research, applied research, in this particular topic. And obviously, George, I think, mentioned about that. And we have a lot of, industry group, teaming up together and supporting a lot of joint research work to, enable AI in airborne systems. So the last point here, right, is the just sort of mentions about the regulatory framework. And so this basically what it says is until the existing regulatory frameworks is validated for its sufficiency and applicability to enable fully autonomous flights of, obviously any aircraft, but in this case, since the roadmap is UAS, the UAS community, obviously, industry and others must use the existing regulatory framework for certification of the enterprise operation of aircraft or unmanned aircraft or any other configuration aircraft. So basically what it says is that so far, right, the popular two regulations are 1301 and 1309 for the other aircraft, and then for small aircraft or Part 23 aircraft, then the sections are slightly renumbered, which is 2505 and 2510. So this is just the continuation of the introductory part of that section. And so anyway, so the scope of this section, right, section 6.11 in this roadmap is to really describe the enterprise level automation as it relates to the technological and regulatory gaps in this ANSI roadmap. And obviously it does not address the technical terminologies and definitions of words such as autonomous, autonomy, AI, automation, because those terms will be created or defined by the standards committees like EuroK, SAE, RTCA, ASTM, IEEE, INCOSI, among others. So it also says that it must be also clarified that there are significant differences between fully autonomous and fully automated flights. Basically, what it is saying is that the autonomy, autonomous, automation, automated, artificial intelligence, machine learning, they all have significant differences, and we encourage all the standards bodies from industry to get together, work as a team to really create the uniform, consistent, harmonized, and aligned definition to map into the existing aviation infrastructure, both air as well as airborne, as well as the ground, covering ground assets. So it is obviously unclear if the current standards on system safety and software, we all know what those golden platinum standards are sufficient to address fully autonomous flight of an enterprise or fleet of UAS that can be launched from airborne, land, and sea. What that means is like if the UAS's remote control station is located in the aircraft or on the land or over water or below water. That's what it means. So, and this is where, right, a lot of these standards committees and a lot of these industry government collaboratives George mentioned, are really like analyzing and, and assessing if how can we address the intended function and the equipment and installation when it comes to the airborne aircraft or airborne assets installed with AI ML in safety critical functionalities. So obviously questions remain whether the existing regulatory framework 1301, 1309 needs to be changed or new regulations need to be added to accommodate fully autonomous flight. So this slide shows some of the operational and aerospace integration related challenges. And while the title of this subtitle is Operational Aerospace Air Traffic Related Challenges, some of these listed items or issues need to be addressed in the design, in the the pre-concept, concept, design, development, and certification phase of an unmanned aircraft. And in some cases, we also have to address in the remote control station. So basically, what we are really saying, on this particular subsection is that a lot of these items, right? We need to address them in the design phase on the aircraft. So, for example, that lost link procedure, item number 4. Even though it's like a operational air traffic related activity, we need to how do we ascertain in the design during design development and certification of an aircraft that we minimize the chance of lost link of an unmanned aircraft systems, right? So this again goes to like the design engineering 101 or system engineering 101 that Barclay had very nicely Barclay and George had mentioned. So then there are other I think there is one, the item number 1 talks about like self-separation, deconfliction, that sort of ties into that detect and avoid that RTCA SC228 is working on. And again, this slide shows the continuation of those lists of regarding operational and aerospace integration challenges. And as you can see here, the last item here towards the bottom, item number 17, the operational risk assessment method and procedures. Will the existing ORA, operational risk assessment and method and processes work to enable fully automated flights of UAS, right? That we don't know. And obviously there is an joint international committee for that, SA18A, Alpha Autonomy Joint Committee with EuroK Working Group 63, Subgroup 1. They are also tackling this problem along with UL 4601. And I believe Joby Aviation, engineer is leading that effort with UL. And then I think ASTM is also working on that. So basically, in summary, right, this AI is a teamwork, and this is not, a lot of people, we have so many programs going on, and we all are really working very nicely. And obviously, George from FAA as the chief scientist is also creating some of his visions and strategies, and he's also investing on different industry public collaboratives like Overarching Property, investing on research, things like that, to really support to really gain the knowledge and also gain the maturity, so that we know so that we will start knowing what we don't know, regarding AI ML in safety critical systems, specifically for airborne application. So towards the end of this section, we have this gap section we call gap, and it is titled Enterprise Operations, using different level of automation, autonomy, and AI. And it states basically, what's the current situation is. And obviously, right now, neither the current regulatory framework nor the existing industry standards support fully autonomous flights at this time. That's why we have a lot of standards committees working to solve, this particular problem in consideration. So just below this, we have this R&D component. In this case, R&D needed, obviously, yes. And then below that, we have three major bulky recommendations. And the first one is basically, it says like, develop industry standards, consensus standards. And the second recommendation is basically, again, just we need to really address the needs of the industry and users, also to guarantee, safety and cybersecurity aspects of AI, ML in aviation. And obviously, the last recommendation here is, we talk about the taxonomy definitions, terminologies, and obviously, we all know that any committees we, create or we try to develop standards, we always, have to define the definitions of the terms and taxonomies. And this gap is priority rated as high, and we kept this as a tier 2. Tier 2 means, I think, like a 2 to 4 years or something like that. But high priority means, this is high priority. And we use the quantified prioritization metrics to calculate the priority. And this slide shows the harmonization of different AI activities that is happening across the globe. And obviously, the first one is the ANSI roadmap version 2, section 6.11. And but this section, AI section in roadmap is at a very high altitude, 60,000 feet, almost like that. And then, close towards the runway type of detailed, technical report is this AFE 87 machine learning. And it is, again, supported by, obviously, George from FAA, as well as industry, Boeing, Collins, among others. And this deals with very technical details, right? But it's still not, this is still not the complete solution, right? This is just one of the solution, And obviously, this is, hosted by AVSI. They are based out of Texas A&M University in Texas, USA. And then we have on the right side, NASA's upcoming NASA Autonomy Verification and Validation Roadmap and Vision 2045. And this roadmap addresses the verification validation for AI-enabled autonomous aviation system or airborne system. And obviously, these are the three major activities for AI ML for airborne or aviation that have been developed by industry group as a team, big teamwork. And this slide shows the scope of the version 2 of the ANSI UAS roadmap. And as you can see here inside this green square box, section 842 through 845, these 4 sections, when the team created last year, we aligned this to map with the existing certification framework, Part 23, 27, 25, and 29. And obviously, this version 2 of the roadmap, or specifically this section 8.4, enables UAS of all sizes, complexities, and operations, leading all the way up to large transport category aircraft. And these are some of the key contributors for the version 2 of ANSI roadmap. Obviously, UAS industry, we have Boeing, Lockheed, Northrop Grumman, General Atomics, Kaman, Honda, Textron, Joby, GE, Rolls-Royce, Collins, Raytheon, among others. And pretty much, all the major regulators across the globe, US DoD, NASA, International Civil Aviation Organization, ICAO, technical experts, and other stakeholders. And this is just to summarize that this is a teamwork. And this was, done by people from 250 plus organizations. And the mission of this collaborative roadmap is to support rapid development of needed industry standards for supporting certification. And the free PDF can be downloaded at www.aviation.gov ansi.org/UASSC. And here is my contact information with my email address. And if you are not able to reach me, you can reach to the organizer or yoga, and they'll be able to connect with me with any questions. And then towards the, after this, we have some extra slides. And that's all we have. And we are really honored to present the work, especially this AI section 6.11. And please, at least, if you can't go through this 412 page long, please go to this one section in the roadmap, section 6.11. And this section has pretty much listing of everything and anything and all the entities that have been working, trying to solve the AI in aviation ecosystem problem. Thank you. Have a great evening, good afternoon, good morning.
Thank you, sir. Thank you, sir, for enlightening us with the major aviation AI activities. So in the interest of time, please, could you answer the queries of our audience in the chat?
Will do. Thank you.
Thank you. Thank you. Our next speaker is Dr. Seema Chopra. She is working as Global Technical Leader, Principal Data Scientist, Data Analytics at Boeing Research and Technology India. She has been recognized as the part of Boeing Technical Fellowship and became Boeing India's first Associate Technical Fellow for Artificial Intelligence. Her current focus includes developing next-generation advanced health management technologies using analytics and big data platform to process the large data in cloud and on enterprise cluster for commercial and defense applications. Please welcome Dr. Seema Chopra to deliver the track keynote address. Over to you, ma'am.
Thanks, Ankita, for the introduction, and thanks for giving me an opportunity. Let me see if I'm successful to share my screen first.
Yes, please.
Okay. Are you able to see my screen?
Yes, ma'am.
Okay, perfect. Thanks for this opportunity. So I will be covering mostly how we are using artificial intelligence, machine learning for aerospace systems in Boeing. And my talk will cover the different applications as well as, maybe we will deep dive in one of the application. Okay, so to start with, can you guess from how long Boeing will be using AI ML? Okay. So I know if we were in a room, we could have started interacting, but Boeing has around half of a century of year experience with AI ML expertise. And we could not design, test, and produce. You can see design, test, and produce and maintain our aircrafts without AI ML. We had a position in 1992 for artificial intelligence lead. I remember I met one of the senior tech fellow like that. So you can imagine from how long Boeing is working in this area. And we work for the AI ML is used not only for our customers, we use it for ourselves as well as for our customers. Okay, so what is motivating to do that? What is happening behind that? So the digital transformation of our aerospace systems. So because of that, we are generating a real-time data, and the data is increasing. So this is one example I'm showing here. You can see this is the in the past we had very few sensors, and then today the sensors are increasing, and future it will be more and more data opportunities. And this is just I'm showing for the aircraft, but you can imagine from a 104 years old company, how many if I think of manuals or the knowledge in terms of text, that is also available. And then all my colleagues, other speakers has already talked about the image data. So a lot of images are also available. So that is motivating us to do you apply AI and IML for automation, for decision making, and so on. So I'll cover some of it today, but there is a lot of opportunities in AI ML. Now, what are the challenges when, so in the past, how the data is increasing? I just want to tell you a little bit of that as well. So yesterday, what used to happen is when we were in the real time, the data was, we used to store the snapshots of the flight data, or the flight deck effect. FDE is the flight deck effect from a few flights. So it was like, it was not a problem. Volume was less, variety, velocity, you can maintain easily, right? But today and tomorrow, historical full flight data, we look into full flight data from the time, it has started from, the flight started from, say, India to US. We want to track each and every sensor and every second data. So it is increasing, right? And then for how many flights are flying at the same time. So you can see. So, so we have, you can see here, volume, variety is increasing now, and velocity still it's like down, but you can imagine the day after when, completely we are acting on every second data in the real time, for example, then you have to act fast, right? If I'm flying and then I have to act fast. So currently you will see, okay, most of the flight landed and I have to give an answer in say 20 minutes saying before I fly, is there a problem or is there something I need to change? So those type of things we are doing currently. So that, when you are ready for the next flight, we should able to predict what fault is there or something where you can, the maintainer can act. So, but so in future we have volume, variety, and velocity. That's how, how to handle all these data and take fast actions. That's how where cloud and other Hadoop cluster, which was in the past, now mostly cloud is coming in the picture. I'll touch upon that in the upcoming slide as well. Now, you see this is AI/ML conference today. But I always say, okay, what is AI/ML data analytics? It's all, the goal, what is the goal behind that is something is very important. Either you apply AI or ML or you do simply data analytics. What is your goal behind that? The goal behind is whatever we say, but we want to convert that knowledge, convert that data into an actionable insights that generate value. So most of the companies where you have like, you will see the data driven solutions, but in Boeing we work together like AI/ML expert along with the subject matter expert. There is a handshake between both of them. So what we start with is we use raw data. You will analyze the raw data and then, examine, correct, validate, format, refine that data. Then you will have, so that is something AI and ML experts will do. And then they will do the exploratory data analysis and apply some machine learning. And then they will, come up with something very interesting. Then, subject matter expert will look into it and then they both talk, okay, this is how it makes sense or doesn't make sense. So they work together to create the value. So by working together, we have created new opportunities for improving operations, efficiency, safety, and economy. If I have touched upon one other thing in the analytics we used at Boeing is, so we are trying to have analytics in 4 ways. One is like, an event occurred and you have identified problem identification. Like, can I, whenever the event occurred, using AI/ML or analytics, can I figure out what is that event? And then the next step is, why did it occur? Can I do a root cause analysis and identify what was the root cause? Why did it happen? Because we want to avoid that. Now, is an event going to occur? Now, the next step is, can I predict it? Like, can I predict the problem well in advance so that, we avoid this? And then what action will yield the best outcomes? Where is the problem prevention? How can I prevent the problem? So that will generate in value. Every step you are generating in value. So what are the type of analytics we use here is the descriptive analytics, which was like for a problem identification, then diagnostic analytics for root cause analysis and solution, then predictive analytics for the problem prediction, and the prescriptive analytics for problem prevention. And how it goes is like you have the data, you have a customer needs, we work closely with the customers, and then you manage the data either in any servers or the cloud or wherever, and then apply these analytics, and then that's where the decision comes. And then have actions, and then they either improve in productivity, dollar value, and that will give the benefit. Now, how other ways analytics deliver value to Boeing is, one is you can see example here, the modernization of the Boeing Renton factory. So this is how our factories looked like earlier, jig assembly. But after applying AI, ML, this is how our factories look like. This is a moving line assembly. So what we have done is we have reduced the factory cycle time, cost of quality reduction, and the covered floor space reduction. So this is the way today our factories look like, and you can imagine how much the fast we are able to deliver because of this moving line assembly. Now, this is for ourselves. As I mentioned, we do analytics not for ourselves as well as for our customers as well. So this was for ourselves, and how it is helping to our customers. So airplane health management, it's a data-driven Boeing designed software service. You can do a Google search. You will find a lot of things. What is airplane health management and how it is helping? So let me give you a scenario here. So for example, there is no AHM. So and the flight lands, and then you're on ground, and then pilot will give the report, and it will diagnose, plan, and fix. So you are on the ground from here to here, and then your next flight is happening. Now, how airplane health management is helping? We have we have a real-time AHM report. A pilot can provide the real-time AHM report. We are able to diagnose, and then we are able to plan it. And as soon as you land, I know which part has to be replaced, what I need to fix it, right? So then it reduced the time, and then you're ready for the next flight. You can see here how much time it took earlier when we didn't have AHM, and when we have AHM, how we are able to save time. And not only this, because of AHM, our customers can see their whole fleet as well. Now, let me tell you a little bit the technology behind AHM, what is happening behind AHM, what we do behind AHM. So we have a flight recorder which records the data, and it will record not only the time series data, it will record all the sensors, like how many sensor any guesses how many sensors? You can put it in the window. I will have a look on it. How many sensors we have in the aircraft? So we record all that data. And then you have like if there is any active fault there, is there any fault occurrence? So that also it sends to the ground, and we have that. And the data comes in, the binary format, and you have to convert that first into engineering units. If it's a pressure or temperature or valve opening or something, right? You have to convert that into a respective engineering units. Once you have that data transferred, processed, then the next step is data analytics, where you analyze using statistics and the machine learning, and try to understand the data. And then we goes to the diagnostic and the prognostic. As we already discussed, that diagnosis basically to identify the root cause analysis, and prognostic is to predict. Both are beneficial. Diagnosis because it helps again to reduce the time if I have diagnosed the root, identify the root cause, and if predict, definitely it helps to the customer to basically whenever there is an unscheduled scheduled or planned maintenance, they can fix those things. So when we do the diagnostic and the prognostic, we give this that goes to the decision support, where the maintenance action assistant and the flight availability evaluation happens. They will understand, and they will see what they want to do. And then this is the health management, effective communication, and the real-time support. And then it goes back. So we also provide information. For example, if a fault is occurring again and again, should be provide the information to the design? Can we do some design improvement? So that information goes back to the design as well. So this whole cycle is airplane health management, and you can very well correlate it with, so we are kind of a doctors of airplane health management, airplane. Similarly, what's the simple doctor when you go for your test as well? What doctor do is the similar things. So you will what doctor will do is, you can think of your health management with the airplane health management. It's quite similar. What it will do is, when you go to doctor, it will take your some sensors in terms of some value from you, like blood samples or BP and so on, and then he will analyze, and he has a normalized value, and then it will say what so he pre-process the data, and then he will trying to understand where your parameter lies, and then he will try to diagnose or predict. It will tell you what, so a doctor will tell you, hey, I see there are these parameters changing, and then you have to either change your lifestyle, or you have to start taking this medicine, and that type of decisions they take after that, and they will predict, you're prone to sugar or something, they will say. So this is complete cycle, like our health management. It's easy to remember if we think that way. So that's about airplane health management. And let me show you one application here, one example what AHM has helped with the powered by predictive analytics. So this is now one of the example for the integrated drive generator on a 777. And so there was so due to AHM identified a precursor event, and we were like the simple way, like released, create, test and verify, validated, develop. The similar way, like you take the sensor inputs, OEM knowledge, statistical analysis. We did all that, and then we released this. But for this the alert, what AHM has predicted, it was able to save around this much in the repair cost. So that's one example, but there are many examples like that. I have been personally working on AHM, so there are many such examples which are there. Now, I want to tell you one more thing, which is Boeing Analytics X. So this is also Boeing's platform, which provides end-to-end analytic capability, which can actually analyze. You will have similar solutions like AHM or crew scheduling or something. Along with that, it allows you to do self analytics as well, self-service analytics. So the good part of Boeing Analytics is it is providing end-to-end capabilities, and all the data, you can see navigation data, crew scheduling, flight planning, flight deck. So all this it is analyzing, and all that data, what we are trying to do is we are trying to put that in the cloud. Because as we talked, right, as the volume for us is increasing, velocity is increasing, so we are moving everything in the cloud. And the good part is we are trying to connect everything as well. So otherwise, what happens is, if you're trying to solve any AI ML problem, what happens is, I do have all the time series data, but I don't have, when the fault has occurred, or when, the airplane configuration, I want to understand from when the part was installed and why this problem. So the good part here is, when if everything is connected, say like this, then you will be able to analyze quickly. So so this is something Boeing Analytics X is providing, and all the solutions are in cloud, which will make it faster as well. Okay, so let's talk about few other examples. This was very specific, but I want to give you a thought process how we are using AI ML to make our products better as well. So what we are trying to use is, we are trying to design our products like, how my product will look like by using AI ML. You can able to think that way. How will my product operate in the field? What should be my optimal design? Or how will I know my design will work or not? So those type of questions we are able to answer using machine learning, AI. How can I collaborate on my design? So this is helping to design a better right product. Now the other thing you can think of is, how are we solving other problems? Like, what can I expect? When can I expect my airplane to be complete? So any guesses how many days it takes to assemble an aircraft? Again, I'll look it in the chat window. Feel free to write something there. So, but but this all giving me insights that when can I expect my airplane to be complete, so that I am well ready for all my orders and all that. The other way is, where can I reduce inspections? AI/ML can help a lot there. Where can as I gave an example of, AHM, for example, or the problems we are solving. So if I have done a prognostic, I know that, this fault, my system looks okay, the complete system looks okay, then, can I reduce my inspection? So those type of things. When does tool life begin to affect first pass quality? So a lot of questions, how can I help all that? That is where you can think, this is just a thought process I want to bring in this audience, that how different ways you can use AI/ML. How can I open up engineering tolerances? Where is my highest risk cell, and what can I do to reduce the risk? And so on, in the cost of engineering worth. So this is how we are trying to make our products better and deliver better. This is how we are trying to use. And when I say these questions, we have answers there as well. We are working on it. It's not something we are thinking on it. Now this is again, this is how AI/ML can produce better. For example, here, like, what has failed on my aircraft? So we already talked about it. So if I can if I know in advance when you are flying, and that what is then I can be ready for that. Or I can if I have predicted well in advance, I know that I can still fly 12 more flights, I will be able to act upon it. So this is what will fail on the aircraft and when. So if I can do the prediction prognostic, that will help, right? And there are some certain algorithms, AI machine learning based in AHM, and which is on the aircraft. And how can the training efficacy be improved while reducing the cost? What parts are needed? Where are they located? So this is another different problem, right? So what are the parts needed, or where are they located? Here you can even use image processing to identify where the parts are located, or my parts are getting over. What should I do now? The asset management point of thing. How can fuel burn be optimized in the real time? How can legacy aircraft capabilities be enhanced? So all these answers, IoT concepts or the analytics or the AI/ML can help in aerospace systems. So yeah, so one more. So here, like advances for new and innovative capabilities. We already heard about little bit about this in the first talk today. How do we enable fully autonomous behavior? Can we do that? How do we ensure our system are trustworthy and secure? This is a very important point when we work with aircraft company or aerospace company. We have to make sure that we are trustworthy and secure. So a lot of work in blockchain AI is happening. How can help our customers to optimize their operations? How do we develop efficient wireless networks? This is also an important area where AI can support a lot. How do we maximize the sensor performance? How do we really deliver reliable communications? So these are the different innovations to enable advanced capabilities and enhance the performance. So these are some thought process, but we already heard about the autonomous inspections, autonomous aircrafts, but this is another example which AI can enable is the autonomous inspection, boost safety and productivity. Can a drone help me to take all the images during the inspection? And can I do, instead of a person sitting there, can I use those images to identify where the problem is? Can I then use those images to identify, hey, whether this, whatever the damage I found is, whether it is allowed to fly again or not? Can I use a lot of questions you can think of? If I take those images and identify, hey, this is the crack, this much crack. Now the question is it allowed? Can I fly back? Then you want to understand the limits, what is allowed or what is not allowed. And then you want to validate it with the maintainer or something, and then generate a report. All that can be done automatically. So there is a limitless possibilities using AI/ML. This is my last slide, and I want to just, you keep thinking, this is I just gave from the aerospace system perspective, but AI ML has really a lot of possibilities which we can enable. And you keep thinking in that direction and see what you bring to the table. Thanks everyone. So this is my last slide. Any questions for me?
Thank you, ma'am. Thank you very much for the engaging session. We do have a lot of responses from the audience, and we also request you to share your answers for the queries from the audience in the chat box. That will help us to publish that. Thank you.
Okay, thank you. Thanks everyone. Bye-bye.
Thank you. Okay, so moving forward, we are now privileged to have distinguished personalities with us to share their thoughts on certification and regulation aspects of AI, ML, and safety critical system. We are honored to have with us today Mr. George, Chief Engineer, Honeywell, as a moderator. I would like to invite Dr. Yufeng Yu. Dr. Yu is a senior researcher with the AI tech team of Boeing Research and Technology. He has more than 15 years of experience in AI, machine learning, safety certification, cybersecurity, formal methods, and model-based engineering. We have Dr. Ali Raz. Dr. Ali is an assistant professor at George Mason University Systems Engineering and Operation Research Department, and an assistant director of Intelligent Systems and Integration at the C4I and Cyber Center. Welcome, sir. I invite Dr. Tom Farrell. Dr. Tom currently leads the Digital Development Assurance Group for Joby Aero. In this capacity, he is responsible for overseeing Joby's compliance activities for DO 178C, DO 254, and ARP 4754A. Next, I would like to invite Mr. Adishesha. He is an engineering leader with 30 years of experience in a premier research and technology organizations like ISRO, DRDO, Honeywell, Philips, and currently with Collins Aerospace. Welcome, sir. Next, I would like to invite Dr. Tom Melham. Dr. Tom is a professor of computer science at the University of Oxford and a fellow at Balliol College, where he tutored in computation. I would also like to invite Mr. Paul. Mr. Paul has more than 40 years of experience with systems and software development, integration, verification and certification of propulsion engines and APU control system and flight critical avionics. I take immense pleasure to welcome the panel of today's session. I now request Mr. George to lead the panel discussion. Over to you, sir.
Okay, thank you, Ankita. So good morning, good afternoon, and good evening to all the participants. We had an excellent, hope my audio, video, everything is good.
Yes, sir.
Okay, thank you. Yeah, we had excellent sessions yesterday, including very enlightening panel discussion on the AML application in safety critical systems, covering the challenges in developing the learning systems for such application, and a little bit on the validation of the system as well. Also, we heard about the readiness of simulation tools. In general, as of now, my opinion is many in the industry have mixed opinion or concern about application of learning systems in safety critical area. However, as we see AML systems solving traditional problems in more efficient way, we can't stop it from AML coming into the cockpit because it makes life a lot easier, better. So maybe we'll start with less critical applications with pilot in loop, but sooner or later we'll have it. And I saw a lot of questions on the chat that George Romansky was trying to answer. So one area that concerns many in the industry, the confidence in demonstration of the level of safety required for such applications in the cockpit. Today we'll focus on the challenges around verification validation for demonstration of system safety, as well as on the certification of the learning systems for safety critical application. We will also share our opinion on the readiness of regulatory guidelines, also readiness of verification tools, though we heard a little bit yesterday. So the methods to achieve the required level of confidence. With that background, I would like to invite the panelists to share their opinion in the subject. I would start with Dr. Yu. So let me ask the first question to Dr. Yu. Dr. Yu, you were involved in many studies on this subject, done at Boeing in collaboration with NASA, DARPA, and FAA. Could you share your opinion on how do the major aircraft OEMs view use of learning systems in aircraft and UAMs? Do the aircraft designers feel safe to introduce AI into the cockpit? What's your opinion? Dr. Yu?
Thank you, George. Can you hear me?
Your voice is a little feeble.
Can you hear me now?
Ankita, do you hear Dr. Yu well?
It's slightly feeble.
Yeah,
We do hear, but it's slightly low. Yeah.
Okay, let me change. How about now?
Better. Maybe you can talk louder so everybody can hear.
Okay. Could you talk with the second panelist?
So we can hardly hear you.
That I change my microphone quickly. Hello, can you hear me?
Yeah, better now. Maybe you can keep the mic closer.
Could you
George, he's asking in the chat to go to the second panelist so that he can change a
sure.
microphone.
I will change my microphone.
So, Dr. Yu,
Hello?
we are not able to hear you. Maybe I would ask the second person by the time. Let me hope your audio will get better. So I would we ask Tom Farrell on some questions on this subject. Tom, you have authored many certification standards for safety critical systems for application in aircrafts. In general, there are optimistic and pessimistic opinion about leveraging AI for safety critical applications that we have heard yesterday also. What's your view from the regulatory point of view on the readiness to accept intelligent systems into the cockpit? Are current standards sufficient to enable use of such system in safety critical applications? What's your opinion, Tom?
Hello, can you hear me okay?
Yes, very well.
Okay. So thanks, George, for the question, and thank you for the organizers of this conference for inviting me to participate. I do want to say two quick things at the start. Number one, I have not earned my doctorate. I have been in the industry for about 32 years at this point. So lest I tip my hat to all of you who have that esteemed title. And I also am a FAA designated engineering rep, but I certainly do not speak on behalf of the FAA. I will leave that to George Romansky and others who wear that badge. Your question had to do with the prevailing standards. And particularly, I have taken this question to mean the DO 178, DO 254, and ARP 4754, which govern how development assurance is actually demonstrated for supporting a certification effort. In short, my answer to your question is no, these documents are not adequate. They have served us very well over time, but they depend heavily on concepts of functional requirements traced through to the implementation with corresponding verification at each stage of a development. Typical learning systems start with operationally focused requirements for which the implementation is accomplished in ways that do not lend themselves to the traditional development and verification approaches. We need new thinking and a new paradigm for demonstrating confidence that AI and ML systems and software will operate as intended under all foreseeable operating conditions. So the community right now is responding to this challenge through industry efforts such as SAE Committee G34, specifically focused on how we will certify systems that include artificial intelligence. There's also been work for many years being accomplished by a small group of folks led by FAA and NASA on what we refer to as overarching properties, to try to tease out from documents like DO 178, what are the overarching properties that we have to satisfy? Things like correctness and intent. We're going to need to integrate these concepts together, both the conventional and those that are under development, to confidently assure AI applications. So from Joby's perspective, the company that I am working for now, we really believe that this is going to be an evolutionary versus a revolutionary type approach. We're going to have to take small steps, and it's going to involve a lot of close collaboration between the regulator in finding compliance and the industry efforts that are having to show compliance. And I noticed that Seema from Boeing finished her talk with a slide that talked about the limitless possibilities of AI and ML. And we agree wholeheartedly with that. But we also would say that AI and ML in the cockpit, and very specifically for fly-by-wire systems, really represents kind of the last frontier. It's probably where we will get to after a lot of these other problems have been solved. And I guess I'll finish my remark for this particular question with a statement that says, you know, AI and ML, yes, it's been around for a while, but in terms of active research and really starting to find its way into industry, it is the latest shiny object. And as a result of that, an old aphorism kind of comes to mind, and that is, if the only tool you have is a hammer, you will start treating all your problems like a nail. And right now, AI and ML is the shiniest hammer we have. So we're trying to shoehorn a lot of problems in that direction. Some will fit, others may not. So just a dose of pragmatism as we launch off on this.
Thanks, Tom. Interesting thoughts. So let me ask the next question to Professor Dr. Tom Elham. Professor Tom, you and your students have been conducting research in the field of formal methods and testing AI. Could you brief the audience about the latest research undertaken in the premier institutes across the world in the field of verification of learning systems? Where is the research heading to?
Okay, thank you very much. I'm going to preface my answer by saying that, you know, the deepest part of my background as an academic has been in formal verification of hardware, microelectronic hardware designs. I've been doing this for 35 years, and much of my work has been directly with industry, with semiconductor firms such as Intel and ARM and others, and also the EDA companies that supply the verification software to them. And I'll say that, you know, in the late 80s, when I got started in this game, you know, everyone thought we were mad and this would never work, right? And it's been, you know, 25, 30 years of slow and steady progress to establish the viability and practicality of formal verification within semiconductor design. There was never a moment where within 1 year, you know, it suddenly became viable, accepted. It was clear that it was delivering value, and so on. And so my view is that formal methods applied to MLAI or systems containing MLAI may well deliver in the future, but it's going to be a long path, research path, and a path that's going to require lots of experiments and patience. And the thing that we always have to add to the pure research results is the methodology for applying this kind of research within a practical setting. And I just can't overestimate the value, the importance of having the experience and practice in methodology. So having said that, to answer the question a little bit more directly, we and others around the world, formal methods practitioners have of course become interested in machine learning and AI, and there's an explosion of research that's been happening. In Oxford, we've done at least 3 kind of main streams of work. One is the immediate application of formal verification, formal method technology to verifying machine learning AI systems or statistical AI algorithms. And this is the interesting thing there is what's the specification, right? So if you're going to verify a deep neural network or something, what is the property you're looking for? And I'm distinguishing between verification of the machine learning functionality, what it is delivering, what it's supposed to be doing, and verification of the machine learning algorithm. I mean, that's just ordinary software verification, and so that's nothing new. But verification of the machine learning algorithm is straightforward. But verifying the machine learning function from the point of view of, say, safety, a lot of it is focused on robustness, the properties of robustness. And in particular, there's a huge explosion in interest in adversarial examples, which cause systems to produce the wrong answer in surprising circumstances. And there's been some attempt with formal to prove that under certain situations of good, robust training, you can guarantee that there won't be adversarial examples of certain types at sort of pixel level. And that's interesting work, but I think far from the comprehensive solution we need to get safety results out of formal. Another direction which I think is actually more immediately promising is testing of machine learning systems, and in particular, what in hardware would be called test generation. And we have huge amounts of experience in test generation, concepts like coverage and so on, coverage of tests and so forth. And so some of the research we've been doing here has been using, for example, GANs, generative adversarial networks, to create tests which challenge a machine learning system in ways that perhaps you hadn't thought of before, and revealing new flaws that you'd not uncovered. So testing, I think, is probably more immediately applicable. And then the third direction we've been going in has been it's not exactly formal methods, but it's been combinations of machine learning statistical models with formal methods artifacts. For example, combining deep learning with automata that help control the learning, or other kind of hybrid combinations of formal methods technologies and machine learning technologies. And that's not really aimed at safety certification or anything like that, but just at producing systems, hybrid systems, which can do more interesting things and maybe slightly more explainable things than we have with straightforward machine learning. So there's an explosion of work going on. We're doing a little bit of it, but other colleagues across the planet are doing a lot. I'll stop there.
Thanks, Professor Tom. So maybe we'll come back and ask more questions around the tools to verify. So let me now move on to Professor Dr. Ali. So Dr. Ali, you have been working on systems engineering of integrated autonomous systems and complex adaptive systems. So what's your take on introducing AML subsystems into complex system of systems? Can the behavior of a AML subsystem, the system of systems context, be ascertained with surety? What's your opinion on this?
All right. Well, first of all, George, thank you very much for the invitation and providing the opportunity to speak to the panel here and share my thoughts on this subject. I hope everybody can hear me okay. The audio is coming. All right, good. So, expanding on George's question here, some of my areas of research has been on system of systems engineering and modeling and simulation, and introducing artificial intelligence and machine learning technologies in the system of systems domain. The idea behind system of system, or why it is different than in another, let's say, complex systems, is in system of systems, each independent system individually operates and it's individually managed. But the system of systems sort of comes together because they see common advantages by sharing information, by exchanging capabilities with other systems. So air transportation system is a classical example of a traditional system of systems. Now, as we were talking about artificial intelligence and machine learning abilities here, oftentimes when we look at introducing autonomy into a system, we take a very narrow and an isolated view that, okay, this is my self-driving car and I am going to automate it to drive safely on the roads. But essentially, when you think about an operation of a self-driving car, it has to operate with other vehicles as well, which have their own, let's say, objective functions to accomplish maybe something common, maybe something competing with that one individual self-driving cars. So when we are thinking about introducing AI and ML technologies in the safety critical system of systems, we have to take a sort of broader view of not only my system, but how the overall system of system is going to work. And in that case, there are like really two opportunities. One is that we use AI and ML to, design the next generation of autonomous and smart systems. And then the second is, how do we use AI and ML technologies to better understand now this expanded design space which has emerged from all these various interactions that are inevitably going to take place in this complex system of systems environment. So my research has been focused mostly on the latter side here, is looking at how we can utilize AI and ML to design and build better system of system applications. And there, I think I would agree with Professor Melham here. The approach that we have taken is not only looking at the AI and ML algorithms or techniques that are available, but sort of taking a systems engineering viewpoint on, if you are thinking about integrating AI and ML. Essentially, AI and ML is a very complex piece, but nonetheless, it is a piece of a system or a part of a system that integrates with the other pieces as well. So then how can we use systems engineering technologies to better verify or validate the ML behavior and integrate ML behavior into system of systems? Professor Melham talked about robustness testing. So that's, of course, one of the key areas, using design of experiments or statistical analysis methods to identify test cases and see how AI and ML works. And the recent area that I've sort of emerged on is looking at explainable AI techniques. So explainable AI techniques are looking into, we all know that deep neural networks are there, and deep neural networks are black box model. So explainable AI techniques are trying to look into that black box model and looking into how the decision-making is being performed. If you have an input space and an output space, what features within the input space influence certain mapping towards the output space. So that's an area of I think, a huge interest, and I think explainable AI, along with robustness testing, will become some of the tools that systems engineers will auto use on a day-to-day basis as we are thinking about integrating AI and ML in safety critical systems.
Yeah, so I have one follow-on question from what you explained. I was following the chat. There were a lot of questions on data set validation. How do we make sure the data set is robust enough? A lot of questions that George Romansky was trying to answer. So now that you have worked on these areas, what's your comment on robustness testing? When do we say that we have good enough training set and testing set? What's your take on that? How do we give confidence on the system?
So that's an excellent question too, and I don't think I have the answer ready for it. I think that's an area that we all got to put our head together and see, what would constitute that end product when we say, okay, now we really understand our systems. I think we are making incremental progress towards that goal, by introducing systems engineering methods into developing the data sets, or and performing robustness testing, performing corner case testing and evaluation for those data sets. And I think that will take that systems engineering effort in order to identify, okay, now we have done sufficient SE in order to provide a data set that we can have confidence in our system. But unfortunately, I don't have a solution for it as of now.
Sure.
I would sort of look to other esteemed panelists here that they could share some of their thoughts on this as well.
Thanks, Dr. Ali. So let me now invite Dr. Paul Petra from Honeywell. Paul, you have many years of experience in certifying many complex avionics systems with various certification agencies and very successfully setting up methods and process to meet the certification guidelines in Honeywell. Could you share your opinion from an equipment manufacturer point of view, designer point of view, the readiness to develop and certify intelligent systems that could be applied into safety critical applications like aircraft?
Sure. Yeah. Thanks, George. And thanks to the organizers of this symposium for inviting me to be on this distinguished panel. As we heard earlier from some of the other speakers, AI has been, different forms of AI systems have been on aircraft for many, many years. And from a technology readiness standpoint, the core building blocks for these, I'll call them next generation of ML, DNN type AI systems really do exist today, right? From sensor suites, actuators, processing units, the building blocks are there. And, they are, of course, continuously evolving and maturing at what we know to be a rather fast pace. Honeywell has a broad portfolio of systems and equipment that we provide to our customers. We have a number of new systems in development right now, AI, ML based systems. One of them is a marker-based landing vision system that we're targeting for vertical takeoff and landing aircraft, the VTOL aircraft. The landing system uses camera-based images to analyze markings resembling QR codes to help guide vehicles to designated landing areas. So very, very basic type system. We're actually working on currently 2 versions of this marker-based landing system. One using a more computer vision based system without ML, and then the other with ML. Primary reason for that is, from what we heard today, the certification aspects of an ML-based system are still being established. We have customers with needs that we're trying to address. So the non-ML based system, we think obviously we can take to market and certify more quickly. We do have high confidence that the ML based system will be more robust in many ways. And having the development of this system in parallel with the more traditional also allows us to take our time in developing the tools and the methods needed to, build the confidence in meeting the new guidance that the regulators are still in the early stages of defining.
Thanks, Paul, for sharing your opinion. So let me move on to Dr. Adishesha. Dr. Adi, you have wealth of knowledge and experience in developing and integrating complex safety critical systems. So you have worked from satellites, missiles, healthcare, in aircraft, so many different diverse applications. Could you tell us your opinion on readiness of AI for adoption into safety critical systems? from equipment manufacturer point of view, how confident are the designers in these various applications?
So first of all, thanks, George, for the question. I hope you're able to hear me.
Yes, very well.
Okay, thanks very much to the organizers of the symposium as well for inviting me as part of this esteemed panel. And the question is very relevant. In my observation, the decision-making, rule-based algorithms, and fuzzy logic and so on in one format or the other, AI and ML is used very moderately at various phases of missions of spacecrafts and missiles with very simplified models and for very specific applications and use cases. It has been a history. Otherwise, these missions like space missions, spacecrafts and missiles cannot accomplish their missions specifically in tactical environment without having these decision-making algorithms in the form of AI, ML. So to quote some of the applications for spacecrafts, these algorithms are used in performance modeling and simulations of subsystems and components and verification of the control laws and switching logics of sensors and actuators during launch phase, arbitraging phase, and also on-orbit modes. So these are mostly offline activities, but they are all design tools. Looking at the safety criticality of that, these go through very rigorous validations before they get onto software implementation in the onboard systems. And in the mission mode, these algorithms are used for source selection logics when we have multiple sensors on board and also on the ground segments. Selection of the authenticated data or the source of information is going to be very critical. So there to evaluate the correctness of the data from a sensor and identify the source sensor, perfect source for application and using it in the mission mode. These are used in the on-orbit phase also. In the onboard computer, these are all coded. And in the ground segment and mission sequencing logics, the mission sequencing logics are very complex in tactical missions, so they need this kind of algorithms. And coming to some of the on-orbit mode of the spacecrafts, these switching algorithms or AI is used in a simplified manner of implementation for recovering the spacecraft from anomaly situations like loss of Earth lock or payload anomalies, and then providing seamless services to the end users. Some of these logics are being implemented and used. Of course, on the ground, less critical is training simulators. Of course, the accuracy of simulation is very important, but these are all not kind of mission critical. They can have opportunity for iterations and fixing the models. So model can take, we can take more time to validate the models there and then evaluate the simulation tool in itself. So the training simulators are used in a big way. These algorithms are used in a big way. And coming to the missiles, majoritarily at the design phase for weapon system planning, weapon system integration and simulation and design validations in the terminal phase or homing phase and end game simulation of the missiles, basically interceptors, when they are used for intercepting a moving target, a lot of these algorithms are used. AI basically is being used even at the simulation design and also onboard the system. So the applications are basically for target detection, target identification, and target classification, and engaging the targets at the homing phase and closing the mission. So there are a lot of uncertainties in the engagement. So multiple rule-based and switching of the sensors and the sensors is needed, and also source of information is needed. So that is where these algorithms are used. And recently, I think yesterday, one of the presentation brought out that SM-3 missile was simulated in a completely AI/ML environment, and the battlefield management was simulated, and it was providing an opportunity as a tool to the end users to evaluate the performance of the SM-3 missile and also associated weapon systems in a completely AI/ML environment. It is a prototype, and then the expansion and also proving of these AI/ML systems is in progress. So coming to the aircrafts, I think sufficiently has been already spoken about. I would not go more into, but some of the things comes into is AI/ML has already been implemented in dynamic route planning, and then conflict detection and avoidance, object detections, and health management. Basically, SEMA also talked a lot about prognostic health management and also database tools and systems. And coming to airport services, passenger facilitation, automatic boarding of the passengers, and border clearances, baggage management systems are some of the applications which are already carrying AI/ML onto that. Coming to healthcare, I think I can say that they are the front runners in implementation and leveraging the potential of AI/ML in various aspects, like patient monitoring, and then patient history selection, and extracting those things at the time of procedures, and equipment operations, in the sense operation of the equipment for critical procedures like imaging systems and so on. The doctor needs very quick orientation and configuration of the equipment. So there these AI/ML have been already implemented and they are in service. And when I say the criticality and acceptance and also going forward, I think when we want to bring it in a larger scale and intensive AI/ML engines onto these systems, I think this needs to be modeled and validated carefully, and then they need to go through rigorous tests to ensure robustness and certification. There is a lot of effort is there, and also a lot of opportunity around all this.
Okay, thanks, Dr. Adi. So I believe, similar to what Paul said, so the opinion is like we already have AI/ML system in some form or other in these areas. Okay, so we'll hear more from you. So let me get back to Dr. Yu. Dr. Yu, your audio problem solved? Can we hear
Hi,
you?
George, can you hear me?
Yes, very well. Thank you. So
Okay,
let
great.
me repeat the last question. We were trying to figure out now, so you were involved in many studies around verification and testing of AI systems in collaboration with NASA, DARPA, and FAA. So what's your opinion on how do the major OEMs view as AI/ML is ready to get into their cockpit? So what's your opinion, Dr. Yu?
Okay, thank you. I'm sorry for this audio problem, probably also video. And thank you for inviting me in this conference. I'll just share my opinion and my comments for these questions. So in general, AI is really considered a game changer in the aviation industry, not by Boeing, but also by all the stakeholders in the industry and the government. So if we consider the future aircraft, we will have less pilots in the cockpit. For example, one single pilot or even no pilots at all in the future. And with AI, it's a great opportunity to reduce safety concerns that can be caused by human pilots, right? But there's still a lot of challenges related to safety. And this is one area that I'm currently working in. And I worked with, currently I'm working with a lot of project in Boeing, some other external project collaborations with DARPA, NASA, FAA, and academia. Currently, the assurance technologies are not yet ready or matured enough according to our current safety requirements and the regulations. But we all, you know, the industry, academia, government agencies are working very hard for the development of these assurance technologies. And also AI standard and its acceptance in our society. So currently, I think at this moment, all the industry are really motivated to develop the technologies, but its acceptance will be a long way. So we will progressively have the matured technology.
Okay, thanks, Dr. Yu, for your view, readiness to accept the technologies into cockpit. So let me now go back to Tom Farrell. Tom, from regulatory point of view, what's your take on evidence for correct operation? That has now been a point of discussion all over, and then people are concerned also. What's your opinion on that? What do we have? What have to be done? Do the regulatory feel confident of laying down guidelines for development of such systems and to demonstrate safety assurance? What's your opinion, Tom?
So this is really the main focus of a lot of the industry efforts right now, is to try to arrive at a similar level of confidence in these systems that we enjoy with the more traditional approach to development and directed testing. As I said in my initial remark, I think ultimately the answer here is going to be many different things layered together to ultimately demonstrate the suitability and confidence level that we need. That may be the application of formal methods for things like reachability analysis. It may be the comment that was made earlier about having a lot of adversarial test cases built into your verification suite, so that you can assert a level of confidence in the robustness and resilience of the system. I can also say that there's been a lot of attention given within the standards bodies, particularly ASTM. They've had a release standard for a while. I think it's 3269 for runtime assurance. So this is basically a very sophisticated monitor that you would wrap around an AI ML system. The challenge there, and I guess I may go a little off topic from your question, because this is and in particular the regulators are approaching this problem, is if we head down a path within the standards making effort where we're going to require very sophisticated monitors, we risk heading down a path where we are effectively putting dual systems on the airplane in every case. So one that employs a solution which may give us better efficiency and overall better performance, but at the end of the day, since we cannot exhaustively prove that it's going to work under all scenarios, we have to put a runtime monitor on, which takes significant resources to develop, and in some cases may in fact lead to less safe systems, because now you have to consider the interaction of the monitor with the primary means of providing that function, and both false positive and false negative cases of the monitor taking over when it shouldn't have, or not actually recognizing there's a problem and interceding in the provision of that aircraft function. So from my perspective, I would say the answer lies elsewhere from a purely runtime assurance approach for ultimately gaining regulatory approval of these systems. So it really comes back to coming up with the appropriate mix of development and verification approaches. And I don't think that mix, by the way, is necessarily going to be the same in all cases. It may be very different for a perception-based system, such as the one that Paul was describing for marker-based landing, and more of a traditional state machine-driven control system. The verification layers may look very different. And I guess I'll say one last point. Ritesh mentioned earlier that we have involvement in a lot of these committees through a lady by the name of Dr. Kim Wasson. I brought her onto our team specifically for the purposes of exploring how we would approach this for certification. And we are very, very optimistic that we're going to see more adoption by the regulatory bodies of an assurance case-based approach for certification, one that is based on structured argument, where you can bring different elements forward and not just a specific prescriptive approach as is defined in DO 170 or 254 for a particular life cycle activity or phase. So I'll stop there. Hopefully that helps.
Yeah, thanks, Tom. So to make sure that we have a few minutes at the end for Q&A, I'll go around quickly. So let me go to Tom, Dr. Tom Elam. So Doctor, we talked about the research in the field of formal methods and its adequacy for testing learning system. So which direction this research is heading to? How close are we to a reliable method of testing AI systems? Are the formal methods mature enough to prove? How are the mathematics, algorithms, tools that are available today to prove the learning systems accuracy? So what's going to be the focus of future research? Could you share your view, Professor Tom?
Thank you very much. I'll be very, very quick here. So a lot of the current work, and I think the panel is almost converging on some of these ideas here. It's interesting, actually. But a lot of the current research is on testing a robustness and evaluation and accuracy of the actual machine learning component. Okay, and unfortunately, none of that is sufficient to guarantee system safety. So robustness does not imply safety, right? Robustness is not something robustness is something we want, right? But it's different from safety. And I think the current research is focused on this, and we haven't. So can we provide confidence now? I don't think so, right? I think what's needed is to take a step back as already been mentioned a couple of times, to think about this from a systems level and to realize that our machine learning models will be embedded in larger systems, and the safety of that system is a whole systems property. And there may be some formal analysis that helps in the analysis of the safety of the system as a whole, or some of our testing may contribute to it. But I don't think there's a kind of magic bullet of formally certified correct that we have in the classical case without statistical modeling that will transfer over to the statistical modeling domain. And so future research really needs to look at safety and of the system as a whole perhaps with machine learning components. And in doing that, if I were to do that kind of research, I would take a step back and I would say to myself, why are we putting a machine learning component into this system? And the reason for that must be one of two reasons. One is we don't know how to specify the required output of that component. So we're going to make a statistical model that will do it for us. Or we know how to specify. So an example is image recognition. You don't know how to specify what the correct pixel values of a cat are, but you can make a cat recognizer. Or we do know how to specify it, but we don't know how to write the program to do it. Take, for example, playing Go. The rules of Go are perfectly clear, but a statistical AI can learn to do it where we can't program it directly. So we have to study the AI in the context of a system, and we have to ask ourselves, why are we putting the AI into the system in the first place? And what's the motivation for that?
Thanks, Doctor. So let me next ask Dr. Ali. We heard your opinion on AML in system of systems. You also said that your area of focus is monitors. So what's your opinion on AML systems that are used to predict the behavior of system of systems? How safe and reliable are they? What's the direction in which the research is heading?
George, yeah, I'll be quick here. But I think as I answered that question, I'd like to follow up on what Professor Melham was saying here. And I think the panel is converging on some of the core ideas. And we had this really neat discussion on what's the state of the art in AI ML at an AIAA panel a couple of years ago. And they started talking about this idea of perhaps maybe we are thinking about verification and validation of AI ML technologies the wrong way. I mean, we never talk about verifying or validating a pilot behavior. So, why are we talking about verifying and validating the AI behavior? Instead, maybe we should think about licensing an AI behavior as an autopilot, just as a human pilot would be. And there are, of course, there is a set of questions that you ask the pilot, and you evaluate their ability to fly on it. There is no guarantee that the pilot is not going to show up, with a drunk the morning of the flight, right? So similar kind of analogy could be used in the AI ML systems as well. So just for food for thought, and I think that just a thought sparked as Professor Melham was talking about it. Now, getting back to your core question, George, about using AI and ML for design and analysis of systems. So I think that's an area of research that I have I've been part of. And the idea there is that you have such a large design space for system of systems that deep neural network methods can help establish the input-output mapping between your design features and the performance outcomes. Let it be the cost, the performance, the reliability, the robustness, and so on and so forth. So using AI and ML to understand your design space for large-scale system of systems, there's a lot of work going on in that field. And they can really help with the design and analysis of a system of systems in identifying the architectures. Of course, we are all familiar with utilizing model-based systems engineering and developing functional physical architectures for our systems, right? But now using AI and ML, we can start looking into that, what features within that physical architecture or a functional architecture or model-based representation really add to the value, add to the performance, or maybe take away the performance. With AI and ML techniques, particularly deep neural networks, you can start to investigate that design space. But going back to your second portion of your questions about safety of those systems, I think that's the same problem we have, is that we can use it to guide our design and analysis and still apply our engineering judgment and knowledge to the solutions. As of now, I don't think we can just blindly trust the solution that is coming out of it without any testing or validation, which has been sort of like a core discussion point among the panel members here.
Thanks, Dr. Ali. So let me now come to Paul. Paul, could you comment if the existing regulatory guidelines and tools and methods are good enough for developing and certifying AI systems for aircraft application, and the level of confidence in certifying such system in the near term? So how confident are we in doing it in the near term? You said there are some systems already in the aircraft, but we are talking about all new method and all new algorithms. So how close are we?
Well, so part of my response will sound a lot like what Tom said earlier. We have the existing traditional standards and guidelines that we are all very familiar with, the 0178C, 254, ARP 4754. These really aren't going to go away, right? They're going to be still needed because these new AI ML systems will still have an architecture that is both core platform, more traditional, and the neural network portion of the system. So I don't see existing standards going away, but we need to augment those. And the augmentation is both in regulatory guidance. Earlier this year, EASA put out their first usable guidance for level 1 ML for public comment. We were hoping to release that, I think, before the end of the year, but we'll have to see where that is. George mentioned overarching properties, which has been out there, and I know a number of companies are looking at that as a technique for assurance of these systems. So we are going to have to use both existing and new standards. I think it was Ritesh that said there are over 400 participants, 200 organizations. Ultimately, it is us as a community, both regulators, industry, academia. We really need to come together and develop what is going to be that new set of standards and guidance that we all rely on.
Thanks, Paul.
Well, I was going to say, existing aerospace companies like Honeywell, we understand the V-shaped development cycle. We've been using it for years. We know that's not going to be sufficient. We do need to evolve that development cycle to something, whether it's the W or something similar. New tools, new techniques are going to be needed to support that new development cycle. And we need to be realistic about the pace at which we deploy this new type of AI ML system on aircraft. They are not as deterministic and predictable as our current systems. And so the overall trustworthiness, I think we've heard that term used a few times throughout the symposium. That's a key factor in the certification of these systems. And then one last point, and it's not specific to AI ML based systems, but the ability for us to bring these new systems to market around the world is also dependent on our regulators harmonizing. The lack of harmonization between the regulators will also be a potential roadblock to bringing these systems to market.
Thanks, Paul.
Sure.
So Dr. Adi, in the similar line, so I have one question to you. So we heard that the tools already we are making slow progress. We need to, as Paul said, we need to leverage the existing guidelines as well as maybe some new guidelines. What's your opinion on the readiness of methods, processes, and tools for demonstrating design assurance of learning systems?
Thanks for the question, George. And then I want to make one disclaimer and a clarification. I need to get my doctorate. I'm in the process of submitting my thesis. So I think a couple of more months. I'm going to get it. So thanks for all that. And then, the question is very apt. Already, the panelists have spoken about the readiness of the tools and how critical it is to evaluate those tools and all that. In my view, tools are available in different domains, maybe automotive and in various formats and various domains. And we are always tending to talk about the speed, efficiency, and progress, 10x speed we want to deliver. So in that process, it is very important for us to marry the domain knowledge with the tools and then validate the tools to 100% and then make them safety assured, and then evaluate all those fault tolerant systems built into these tools, and then validate them very critically with respect to conventional track versus AI ML track, and also having redundancies to manage any of the failure modes while we implement in the critical systems. So these are going to be very important in my opinion. And then we have started somewhere, but we have a way to go. And then as they said, the whole world is working towards it. And we are pretty optimistic that we are going to get there faster.
Thanks, Dr. Adi. So maybe let me come back to Dr. Yu for the last question now before we hear questions from the audience. Dr. Yu, you have made many studies on the verification validation of AI-enabled autonomous systems. What's your opinion on approach to accept such systems into the aircraft? So what is being done for certifying such systems for introduction into the aircraft from OEM point of view?
Thank you, George. Can I share my screen quickly to explain this question?
Sure. So maybe we don't have more than a couple of minutes, but we can share and then talk.
Okay. So can you see my screen?
Yes, we do.
Okay. So I will just explain quickly what we have done for this big challenge, safety assurance for AI and the path for certification. So this is not a standalone effort. We will need to work with the whole industry, community, academic, and the government agencies. And this figure shows our effort from Boeing side, Boeing research and technology. And you can see that we are working currently with the some internal projects in the blue box, and the light blue boxes are the academic collaborations. This is just small list. We also have some other collaborations, and we work with FAA, NASA, DARPA on this big challenge. And after that, we see technologies developed in different projects. We will try to integrate this into the current AI standard under development, including the ANSI UAS-SC standardization roadmap and the G34, SAE G34 UK WJ114 AI in aviation standard committee. And of course, we also consider other standard committees such as NIST, RTC, ISO, UL, STM, RTOE, and the AIA. So from all these efforts, you can see that we are currently have a very broad collaboration, not only in Boeing, but also with our external collaborators and the government agencies and the standard committees. And it's still a big challenge. If we think about the safety assurance, we can see 4 areas. One is the development of autonomous platforms that can be used for the safety assurance experiments, and then the assurance technologies development, certification considerations, and the guidance and the regulations. So to answer your question regarding certification and the regulations, we also have many projects that are working in this area, not only for the technology itself, but also to find out how to use these technologies to be compliant with the current regulations and the future AI standard and the regulations. So we build the processes, the standard, the evaluation metrics, but it's still a challenge that how to find out how this stuff can be used for the future certification. At least currently, EASA and the FAA are developing these guidance and regulations. So we are working with them and try to find the path ahead for certification. And this shows, Ritesh already showed this before, but we want to show that the whole community is currently working together, not only the standard committees, but also the regulators, industry, academia, and we are working together to develop the future AI standard and potentially the future guidance and the regulations for AI. Okay, thank you.
George, we don't hear you. You're muted. George, yeah, you're
Yes.
still there. You go.
Okay, sorry. Yeah, so now that we heard expert opinion from the highly experienced panelists, we will have a few minutes to hear questions that we can answer, get answered from the panelists. So are there any questions from the audience?
I don't see any, George.
Okay, so should I go ahead and then summarize?
You can summarize. Yeah.
Okay. So thanks everyone. So let me quickly summarize what the panelists shared. So we heard from Dr. Yu that the future cockpits are going to be less pilot, single pilot or no pilot. That's very interesting. So that kind of underlines how important that learning systems have to mature. So to take pilots off the cockpit. And also Dr. Yu talked about the industry standards evolving. We are not close, but everybody is working together. And coming to the opinions from Tom Farrell, Tom Farrell said we need to take small steps. So the guidelines are not good enough. The existing guidelines are not good enough. Maybe we have to take small steps, and then maybe we need to have monitors. If we have monitors, maybe another problem would be how do they interact, the monitor and primary, and then that's going to be more expensive and burden. So we don't know, but small steps is what we need to take, and over a period of time we have to get AI into the cockpit. That was Tom's opinion. So coming to Professor Tom Ilham, the professor said, now the formal methods are not yet at a stage to give required confidence. So he was talking about do more testing, robustness testing, and test the accuracy of the system. So that's where the focus should be. Professor was saying that there's a lot of work going on, but maybe the tools are not yet ready to give the required confidence. And coming to Professor Ali, Professor Ali was saying that maybe think broader, not only your systems, the AML system for better. No, he was talking about his research on AML systems to understand the systems better. So how do they behave? So we can analyze it later. Also, you can investigate the behavior of the system if you have monitors. That's what Professor Ali was saying. That's a new thought, really speaking. It would be interesting to read Professor's papers. So Paul said there are already some systems in use. Already for many years we have it in some form or other. The building blocks are available, and then there are some systems evolving, something like vertical takeoff, landing, all those. And also Paul was saying that maybe we have to go with the existing standards plus new. So you cannot totally rely on the new standards, or maybe existing standards are not good enough as such. So Paul was mentioning the current V method may not be sufficient. We have to augment it with the new methods. So coming to Dr. Adishesha, so he was also talking about many AI/ML applications already got into the safety critical areas that he has worked on. So he was taking examples of where exactly these are already using AI/ML. And then he was also of the opinion that we have to incrementally build this system and validate. So this is what we heard from the panelists. So anybody would like to add anything to the summary? Okay, so I'd like to thank all the panelists. It was very interesting, and hope very soon we would have these industry and regulatory all work together, and the universities work together to solve the roadblocks, so we can change the way the cockpit works today, so for the better. Thanks everyone. Hope everyone enjoyed the discussion.
Thanks, George, and thanks everyone for attending.
Thanks everyone.
Thanks everyone.
Many thanks. Bye.
Bye.
Thank you, George, for leading the panel discussion, and thank you, panel members, for taking out time and sharing your thoughts. Now it's time for a short break for about 5 minutes. We will see you at 7:45 p.m. IST. And I also request all the viewers to kindly fill up the feedback at the left corner of the auditorium. Thank you all.
From the smallest details to the highest pursuits, we are redefining aerospace. With our customers, we relentlessly tackle the toughest challenges in our industry. And every day, we imagine ways to make the skies and the spaces we touch smarter, safer, and more amazing than ever. Together, we chart new journeys and reunite families. We protect nations and save lives. And we explore the unknown. We believe in the power of intelligence and partnership to guide our customers into the future, reshaping our industry across the globe and even beyond. The paths we pave together lead to limitless possibility, and the bonds we form propel us all higher, again and again. We are constant in our evolution. We are connected to our customers, always. We are compelling as we boldly step forward. We are redefining aerospace.
In more than 75 years of our partnership with India, we have seen the nation transform and soar into the skies. It's a matter of great pride for us to have played an important role in the mission readiness and modernization of the country's defense forces, a relationship that goes back to the Second World War. A mainstay in the commercial aviation sector, we are connecting India to the world with the most fuel-efficient airplanes. It is here in India that we see the future of aerospace unfold. Innovators brimming with ideas, engineers converting imagination to reality. Leveraging this potential is an incredible opportunity, not just for India, but for the world. Building a local aerospace and defense ecosystem for an Atmanirbhar Bharat. Investing in local partnerships and nurturing homegrown talent. Committed to transforming the communities we work among and creating lasting change. We are bringing the best of Boeing to India and the best of India to Boeing.
When you imagine the future, what do you picture for flight? Do you imagine better future is here, and it will forever change the way we fly. Honeywell Anthem. Experience flight reimagined.
Welcome back, everyone. We are now approaching to the end of this informative two-day symposium. I would like to invite Mr. Shashi Kumar, Principal Engineer, Honeywell, to give us a quick recap of 2 days. Over to you, sir.
Thank you, Ankita. It's been nice 2 days event, and we've been amongst the very knowledgeable audience and the distinguished speakers. So to just quickly have a recap of the day 1 and day 2. So we started with Ms. Kerry, presented the positive and negative aspects of AI and provided a nice example of a wildfire situation and how AI can be used. And we followed it up with Mr. Savyasachi Srinivas, who explained to all of us on how an AI component can act as a third virtual support crew in a battle tank. It's similar to what we have in a, the single pilot operation kind of thing. So another pilot will be virtual kind of thing. So how the support will be provided to the soldier. That's what as a concept of the entire Savyasachi's discussion. Then we had Dr. Satish Reddy, Chairman DRDO. So he said, we're so aggressive on setting up AI groups in all the systems laboratories, and I think their labs are open for academia as well as the funding is available from the DRDO. So they have to approach the universities, through universities to the incubation center for the funds for the AI projects. So that's a very nice welcome move from the DRDO. Then Dr. Ramesh has spoken on the how AI can mislead with biased data that is used to train the with the training data. Then followed it up by Dr. Satish, who gave a quick overview on how math works as a tool chain, complete tool chain to help us develop AI systems. And then Professor Goody spoke on how physics models and PCA can be used to validate AI. So then we have a detailed panel discussion who was moderated by Dr. Daryl. So we had a panel of Kiran Kumar, Mr. Nicholas, Mr. Robert, Dr. Stacey, and Mr. Prashant Rao. So which summarizes, do not use AI if your regular methods works well. Use AI because it is required to be used. So it's not a magic bullet, you can use it everywhere. So it's just because AI is there, we should not use it, because it meets your demand, only then it works for you, then only you should use, otherwise you should not. There are safety concerns with the use of AI. So we are not yet there, yet for the entire AML systems coming up. So that was the conclusion of the panel. So coming to the day 2, and we started with Mr. Mudit, who set up the recap of day 1 and the day 2 context setting. So and give a brief introduction to the INCOSE of India. So the day 2 keynote, we had 3 keynote addresses from the day 2. So the keynote address by George, Chief Scientist, Technical Advisor, FAA. So the main concepts what he spoke on that, what is an AI used for, advisory, control, emergency, monitoring. And most important couple of questions he brought up is how accurate and trustworthy. So, and he also pointed out on the certification and verification challenges, and DO 178 does not support the deep neural networks kind of systems. So and he emphasized the use of overarching properties, which FAA continues to do research for the last couple of years, and they're still working on it. And the other couple of guidances which George has touched upon is SAG 34 and AVSI groups, which are working on them. So that was the brief of George. And he elaborated quite a bit on overarching properties, and seems to be a good explanation of overarching properties. And how he also spoke on how we build trust and what are the proposed use cases which FAA is working on, like autonomous co-pilot, landing, plane landing, clear runway, sense and avoid systems, clear US landings, terrain recognition, follow center line of landing strips. So these are some of the use cases which he spoke about. And also he said, how can we build trust? A couple of areas which it is thoughts on is audit process is one, experience, service history, continuous training of periodic update of the data, and monitoring systems. So that's another area which even the panelists have discussed today on the monitoring systems. So these are the areas where George has touched upon. And in the second track discussion, the SC aspects and certification regulation. So the track keynote address by Dr. Barsley Brown. So the key takeaways from his speech are, system engineers must be aware of role of training data. System engineers must specify data based on the application and environment with collaboration from the data scientists. Key areas are the DADs, that is diversity, augmentation, distribution, and synthesis. So these are the key areas system engineers be aware of it, and they should specify these requirements, the data requirements well in advance, so that they can build proper systems, AI systems. So then the next keynote address was from the Ritish, who spoke about the UAS standardization collaborative approach, UASSC. So especially he spoke about section 6.11 of enterprise operations, level of aeronautical autonomy, autonomous and autonomy, and artificial intelligence. This is the key topic which the guidance which is coming up. So total, so he summarized that there are 3 guidances which will be working on in combination of harmonization for AI activities. One is AVSI, another is standardization roadmap, which is from the section ANSI roadmap. And the next one is the NASA guidelines, which is coming up. So all these guidelines put together will be a good package for the certification of AML systems. That's what is the gist of this discussion. And the third keynote address was by Dr. Seema Chopra from Boeing. So she gave good insights into how data analytics is in Boeing factory to reduce the cost and cycle time, to improve the cost and cycle time efficiencies, and aircraft health management system and predict health management is another area where she felt the Boeing is doing excellent job in using AML systems. And the bottom line is AML is there to produce the products that are for the Boeing. So the dawn of limitless possibilities using AML. That is the punchline which Dr. Seema ended her talk. So in the last, we had a day 2 panel discussions moderated by George Polepilli, which was well decorated by Dr. Yu, Mr. Tom Farrell, Mr. Tom Hallam, and Dr. Ali, Mr. Paul Honeywell, and Dr. Adishesha. So everybody has expressed when the regulations are not in place yet. Industry and regulations are working together and will be a long way still to go for the approved guidances. Boeing's effort, Dr. Yu spoke on the Boeing's effort related to AML safety assurance. And Mr. Tom Farrell has spoken on the overarching properties can be being researched. It will be evolutionary, and not revolutionary. So it will be gradual steps it will come. So you might need very sophisticated runtime monitors, which might not be very cost effective. So how the cost effective runtime monitors, robust monitors to be developed and deployed is another area which Mr. Tom Farrell has touched upon. And Dr. Tom has stated that current research and testing and formal methods, formal methods, it took nearly 30 years to reach the current state, and to bring confidentially deployed in AML systems, it is little while it will take, definitely for sure. And a lot of research is on testing robustness, which is different from safety and on formal methods with AML systems. So Dr. Ali expressed his views on AML deployment in complex systems or system domain. What is about good enough training set is another area which he elaborated upon. And Paul from Honeywell has said that regarding the readiness of to develop and certify systems from Honeywell. So he spoke elaborately on that, and he also gave a couple of use cases which Honeywell is working on. And Paul has commented on the existing systems, existing guidances and regulatory guidelines which continue to stay. Overarching properties, another means. You have to have the existing standard along with the upcoming standards specific to AML. So that's another area which Mr. Paul touched upon is harmonization of guidances among multiple regulators globally. That's another serious area for collaboration. So that's what we emphasized. And finally, Dr. Adishesha has said that readiness for AI adoption in safety critical systems, satellites, missile systems, and aircrafts to healthcare. So he spoke elaborately on that. And most important, Dr. Adishesha stated this: marrying the domain knowledge with the tools, existing or upcoming tool sets, and validating the same is a very important area for research. So that's the wrap up of day 1 and day 2 recap. So Ankita, it's over to you. Thank you.
Thank you, sir, for the recap and sharing the key takeaways. Now may I invite Mr. Raj Pai to deliver valedictory keynote address. Mr. Raj serves as a senior technologist in NASA's Aeronautics Division, where he leads machine learning and big data research areas in supporting the Aeronautics Research Mission Directorate SKY for All initiative and FAA's InfoCentric National Airspace System. It is my pleasure to welcome you, sir. Over to you, sir.
Thank you. And I'm not sure if you can see my screen here. I'm having a little bit of a problem sharing my video. So we'll just go ahead with my shared screen.
Yes, sir. We are able to see your screen. Please,
Wonderful.
could you put it on the, yeah. Thank you, sir.
All right. Can you see my screen? Okay.
Yes. Yeah.
Okay, wonderful. And I just wanted to make sure we are on time. I have exactly 20 minutes, right? 25 minutes?
Yes, sir.
Yes, yes.
Yeah.
Okay, thank you so much, and I appreciate giving me the opportunity to do the last session. I know I may be standing in between your evening cup of chai or cocktails, or if you're on the West Coast here in the US, you're probably waiting for your cup of coffee. So I appreciate you taking the time. My name is Raj Pai. I work as a senior technologist in NASA Ames here in the aeronautics division. I'm going to focus my topic, my speech here on a few things. I'm going to talk about AI and ML in aviation in general, talk about some of the latest trends that we see out here in the Bay Area and in the AI ML industry in general. And then we'll wrap it up by talking about some of the certification efforts that my team and I'm involved in, just really quickly in the 25 minutes. I'm trying to be adventurous here, so there's a lot of slides, but hopefully you'll bear with me, and this will be an interesting session. A really quick introduction to my background. I've been really fortunate to have the front seat here out here in the Bay Area for the last 30 years, working with incredible teams and incredible companies and researchers and academia in the space of computing, PC computing in the early days, and then mobile internet, and now more recently, big data, AI, ML. As we talk about safety critical systems, some of my learnings from the smart grid and energy applications that I built over the last maybe 5 or 6 years back, those are very relevant. Healthcare and drug discovery while I was working at some of the data companies. My current work at NASA focuses on a few things, and I've just highlighted a couple of programs that I work with. I work with the FAA on next generation programs, specifically the infocentric NAS programs that they're launching, which heavily involves the use of big data, AI, ML techniques. I'm also the tech lead for an internal initiative at NASA, which is called Data Information Platform, where we are creating a platform that will accelerate the development of AI ML services as well as data services that are needed by both traditional airline operators as well as emergent operations like US or UAM operations. Really quickly, and I know this is a team, the audience here is intimately familiar with this. So I know the aviation industry is at an inflection point. And I say this in a way because I've been on so many discussions and panels in the last couple of years. The pandemic has really given a shock, a bolt to the aerospace industry. And my belief is on the other side of this pandemic, this industry will emerge more stronger, more resilient, and with new models, new technologies that can be adopted. And I'm excited to be part of the journey. And this is really quickly, most of you must be familiar with this. The recovery post air traffic recovery post pandemic has started, and it continues to be very localized. And I'm sure you see this in India as well as in certain domestic markets. The domestic traffic has definitely picked up. We're close to getting near where we were pre-pandemic. International travel still continues to suffer, but more recently with the opening of traffic in November, I think things are looking good. If you look at any analyst reports or what's coming up, I think there is optimism that we are on the path to a quick recovery here for international travel also in the next couple of years. What's clear is that the restrictions that have been implemented by countries has not been uniform. The rising vaccination rate is definitely hope for optimism. And I think yesterday, India hitting a billion landmark was amazing. And that's really encouraging and exciting to hear about. As we look to the future, a few things are obvious. I think there will be new kinds of travel, leisure trips by consumers like you and I will definitely fuel the recovery. There's an insatiable demand from consumers. Business travel is starting to look up. Public-private collaboration will thrive. And I think these take different shapes and forms. Air India going Private is an instance of that. In different markets, there are different initiatives, either funded by government initiatives or things getting private. So it's an exciting phase for the aerospace industry also. One thing that I uniformly hear when I'm talking to leaders in this space is there is a sense of urgency that IT, automation, digitization is definitely needed as we emerge on the other side of the pandemic. This is not an option. The question that I always hear is, uh, you know, not whether we should invest, it's the question of when do we invest? And that's great to hear. Another question that I often hear, and since this is a panel on the session was focused on AI ML, is does the aviation industry really need AI ML? Um, and I'm sure most of you are convinced that aviation and aerospace industry in general does need AI ML. And I'm not here to say whether we need it or not need it. Just based on my experience working with various other industries out here, whether it's telecom, healthcare, or even in the energy industry, I think the question is not if you need it, it's the question of how soon can you adopt these technologies. Um, and I take a top-down view here when you're looking at it. Digitization is definitely will fuel critical business results that the aviation industry needs to achieve in the years to come. And it's all along all dimensions. If you look at growth, and I look at growth not just in terms of the revenue per passenger, but it's in the growth in terms of new users, new vehicles, new business models. During COVID, I've read reports in India also where drone and unmanned aircrafts are being used for emergency deliveries. Out here on the West Coast in California, NASA is actively involved with various federal agencies to deal with wildfires. I know in other parts of the US, we are also looking at use of unmanned aircraft for medical emergencies. We are looking at emergency preparedness, response to emergencies. So there are all classes of use cases and users and new operations that are coming up. So, and those are going to be fueled by innovations that we're bringing to the table. The second item here, which is key to some of the missions that we're driving here at NASA, is sustainability. As we look at electric vehicles, we look at supersonic vehicles, we look at eVTOLs, unmanned aircraft systems. I feel digitization plays a key role in this throughout the life cycle of these vehicles also, whether it be in the design phase, the validation phase, the development phase, and finally testing them out in real world scenarios. I think digitization, the incremental cost of digitization and using those digitized copies of these new vehicles, whether it be in high fidelity simulations or in actual test runs, the incremental cost of having digital copies is almost next to nothing. So digitization is a key enabler for some of the sustainability efforts that we're driving. And last but not least, as we work with the airlines, business aviation, commercial cargo, running safe and efficient global operations, data and AI/ML services will continue to play a key part. And one of the quotes that I love to say, and I've seen often used in other industries also, is we often operate in an environment of scarce resources or resources that are competing for attention in any industry. But data happens to be one of those resources that is growing exponentially, and it continues to grow, and harvesting that data for whether it's for efficient decision making, situational awareness, or more predictive purposes is one of the easiest ways to harvest an overabundant resource and utilize it for business benefits. I'll switch gears here and talk about some of the trends shaping enterprise AI/ML. And I've noticed this in the last probably 4 years, having worked with various industries and also in the aviation industry in the last couple of years. There's been a gradual shift in how AI/ML is being perceived. And one of the first shifts is it's no more an experimental research technology, especially in some of the folks I talk with. Two trends that I see emerging very quickly. One is this notion of data-centric AI ML applications. And just to start off, AI ML systems, and I know I'm overly simplifying this. What is an AI system? An AI system is really a combination of code plus data. And when I say code, there are very rich models that can be built out. There are algorithms that can be brought to bear. There are amazing techniques that are evolving on the AI ML side, whether it be deep learning, transfer learning, reinforcement learning, various techniques that the big three or big four industry leaders out here, which Google, Amazon, Microsoft are bringing up, and there's amazing work that is coming out of academia. The shift that I see is people are going beyond just these bespoke development models, beyond just having and being done in experimental mode, research and prototyping, to getting into more mainstream applications. And I've seen this in the past, whether it is big data technologies or cloud technologies also. I think we are now getting into a phase where it's enterprise-wide adoption of AI ML is what we heard about. And of course, the initial first step happens to be small projects, small research and prototyping that affect a business process, an entire end-to-end business process that is being implemented. Starts off being small with sample data sets. And I often talk to my researchers and interns that I work with and say, you don't really need big data. Well, big data is a buzzword. You really need small data to validate the business outcomes, the technical results that you're getting out from some of this initial rapid research and prototyping phase. The next phase, which we are seeing and I'm excited to be part of, is the deployment phase. And this, I feel, is the critical rubber hits the road kind of phase in AI ML, where the AI system is, you have these incredible code, you need to customize it for your domain applications. You're using amazing cloud-based technologies. There's lots of open source and vendor provided tools and platforms that are available today that you bring to bear. But the most critical part of it is using it with real data, using it with real operational data, and more importantly, having people. And when I say people, it's humans and practitioners who are on the front lines or emerging new roles that get to touch and work with the AI system. And it's especially true in safety critical systems, whether you're monitoring an unmanned aircraft system, you're piloting an eVTOL, or if you're using some AI ML based software solution that might be available on board a traditional aircraft or a incorporated, a system that's been introduced into an existing vehicle. So this is the critical phase. You have to go through trials, validation, you have to go through experiments, but getting it in front of people who are actually going to be using it is critical. And we are seeing this shift. So why is this, where is this all headed? And there are various frameworks, various models that are being used today. I like this one slide, and it encapsulates very nicely what is the typical AI application life cycle and what needs to happen if you want to make AI ML not just a corner technology, not just a nice to have being done in a research lab, but becomes mainstream. What do you need to do if you're a digital, what does a digital tech savvy CEO do in their company? If you're under the assumption that this is not something that's going to be done in the side, but it's going to be embedded in everything you do as a business, as a technology, and or a research institution. This shows the typical approach, and it's called sometimes it's called the AI factory approach. Just like you would build anything, build widgets, any product in a company, you want to have a factory approach to churning out these AI ML solutions. Starting from the left, it involves data management. In my experience, having deployed a lot of these AI ML solutions over the last 5-10 years in production, data and handling data and working with data lands up becoming the long pole. 95, 98% of the effort, whether it's in terms of human effort or coding effort or validation or whichever way we want to look at it, a big chunk of it is spent in managing their data. And the next part of it is, after you're done with the design, development, research, prototyping, you want to develop this and deploy it. And then finally, the hard part of it, which I've seen in a number of industries, where if you're going to deploy a live model in production, how do you keep that model current as live data streams are coming in? How do you take care of model iterations? How do you take care of model drift? Because the world we live in, and especially in a cyber physical world such as aviation, the data streams that are coming are not static. You have to adapt those models. A key takeaway for me when I'm looking at it is, when you adopt this AI factory approach, you need to standardize on a technology stack. As you move away from doing these experimental AI/ML projects beyond your prototyping stage, being able to leverage a common data framework, a good common data technology stack, whether it be in the cloud or hybrid, whichever suits your business model the best, having a common technology stack becomes critical. It also helps a lot to have this AI factory approach when you're talking about compliance, security, and risk. When you talk about using these reusable assets over and over again, not as a one-off effort, but embedding AI ML throughout the enterprise. And finally, people. As I think during the course of the discussions today, you might have people might have spoken, and there are a lot of esteemed speakers in the panels today. Talent is becoming a key blocker, if I may. We need to train, we need to equip our employee pool, as well as the younger generation who are adopting and who will be the stewards of this new AI/ML solutions and data solutions that we're deploying. It's a critical thing. There's a huge shortage, and I'm sure it's global. It's not just here in Silicon Valley, but it's all over, that we see a global shortage of talent that are data and AI/ML savvy. Investing in that and getting them involved early and often is definitely a key need. I've got about 5-10 minutes here, and being a product person from Silicon Valley, I have to go get into some of the details, and I'm going to take you through a real quick preview of some of the work that we are doing here at NASA. This is just a sampler, something I'm passionate about, and hopefully you will appreciate it and see it in the context of some of your work, and how we could NASA is collaborating with industry as well as government agencies, regulators, to enable key research in this space. I call it Walk the Talk. This is a sample snapshot of how we are applying natural language processing for heritage documents that exist in the NAS. And this is there's NOTAMs, and I'm sure I'm not going to give a technical primer on NOTAMs, but notice for airmen. There are letters of agreement, standard operating procedures, typically written out in various documents. And what we're using AI/ML for that, for these documents, is to extract digital entities out of it and create models. And in a minute, I'll show you what these AI/ML models can be used for. In particular, we're also using a technique called transfer learning. And transfer learning, essentially, at the highest level, is the concept where you have these pre-built models that other industry participants, other vendors, and there are lots of them available in open source, where it has been trained on a corpus of web available data. And the promise here is that you can train these large models, which have been trained on hundreds of millions of data sets and have lots of attributes. You can customize it for the aviation domain and use it for your purpose specific. And in this case, we're using NOTAMs. It can be used for LOAs. We also have some ongoing work for spoken transactions, speech. So you create a domain specific model and use this AI model. And I'm really quickly, this is just a concept, research concept. there is a creation process for NOTAMs, and I equate this to Google's queries, where you can say, I'm being lucky. And if you are an operator or a user that is creating this NOTAM today, you have to remember the syntax. You have to understand the syntax of what gets put into these NOTAMs. The AI ML model that's powering this has been trained on millions of historical NOTAMs that have occurred, specifically in our NAS, National Airspace in the US. And it has learned that if I'm sitting here in SF4, if I type SF, it auto-fills SF4. If there's an obstruction on the, if there's a navigation problem or a navigation issue or airspace constraint, it pulls up a runway constraint, says there's a closure, and it says, it knows that there's a 10R28 left runway configuration. It has learned about this, which are the most common closures if you've ever been to San Francisco due to weather or some obstruction. So that was a quick example here. And I didn't mean to walk you through the example in detail, but an example of how an AI ML model is being built and can empower some of the decisioning. And this, what I showed you was on the NOTAM creation side, but in the background, that's what's happening is the digital entities, digital airspace constraints that have been identified in the NOTAM or in a letter of agreement can now be exposed to all kinds of users, all kinds of operations, whether it be manned or automated in the future. And those airspace constraints can be easily understood. I'm going to, in the last few minutes here, I'm going to talk really quickly about AI ML certification. I know this is a hot topic and was a focus area for the sessions that we had earlier in the last 2 days. I'm involved in an effort in collaboration with the FAA and with industry partners, and we're coming up with frameworks. We're working on how do we implement some of the AI ML certification requirements from a congressional perspective, also involved with a lot of work there. 2 slides, and it's hard to encapsulate all of this in just 2 slides, but I'm going to summarize by saying there is a need for a flexible certification framework that builds on existing software assurance, software validation verification frameworks that exist, and really depends on what kind of maturity level of the AI ML solution that we are talking about. Is this custom off-the-shelf software solution that you're picking up, or is it a brand new solution? The most important part of it is the latter two. What is the impact of the solution in terms of criticalities? What are the AI technologies that are being used? And this encapsulates everything from the data to the platform to the models, the deployment models. There are several nuances of this. Now, another key thing that we look at when we are working with partners and collaborators on certification is what is the level of certification rigor that you need. And this is a quick slide that we use to look at what is the role and response criticality on the vertical axis. We're looking at the AI ML solutions role and response criticality. And on the horizontal axis, we're looking at risk. And this is one framework that we use. And if you go from the lower left to the upper right-hand side quadrant, there is an increasing need for certification rigor. And we start looking at use cases, and we're working with, earlier I saw the SA34 forum, we're working with global organizations to list out use cases as the solutions are coming up. What is the role that AI ML is playing? And from an industry perspective, I see AI ML playing an augmentative role where this is pre-flight, in the design simulation phase, where it's being used as an analysis tool, more as an advisory for a function, playing an advisory function. If you go up, AI ML solutions can also be used for decision-making functions and play more of an assistive role in strategic as well as tactical planning. both for existing operations as well as emerging operations. And then finally, I know there's tremendous promise here if you start looking at how AI systems can be used in collaborative environments where humans, where there's human to system and multi-system interactions. And we look at not just emerging scenarios, working with partners, but also look at 5-10-year scenarios where the concept of operations will be very different. And we work with some terrific people and terrific companies who are collaborating with us to define this certification framework. There is a lot more that that the team is working on. We work with industry academia to define this, and it's an exciting time because where I see the industry headed is AI/ML will be embedded in pretty much everything that you do. And to quote a famous investor here, I think about 5-10 years back, the investor said, software is eating the world. And I think where we are today is it's pretty much a given that AI/ML will be embedded in everything that the aviation industry will do in looking ahead in the 5-10 years. And it's an exciting time. There'll be a new exciting roles for different people and different talent pools in the industry. And I'm looking forward to working with my team at NASA, as well as academia, as well as vendors in the ecosystem. That was my last slide. I know I started off by talking about how the pandemic has affected the industry. We are emerging on the other side of the industry. We are seeing a lot of promise, both from the airline operators, business aviation. There's some really exciting work that we're doing with commercial cargo. We are working with government agencies that are looking at emergency preparedness, whether it's firefighting, hurricanes, emergency medical delivery. There's lots of exciting things that are happening here. And AI/ML technologies, automation, autonomy will play a critical role. And the talent pool that's involved in this, it is a global effort. We are learning from entities from all over the world, and we are excited to be part of the journey. Thank you so much. My email address is there. I know I went through this really quickly, and coming from the West Coast out here, I was not able to attend some of the earlier sessions, but I do look forward to interacting and working with many of you in the future. Thank you so much.
Thank you, sir. Thank you for the insightful valedictory key address and sharing the trends, AI factory approach, AI/ML certification, and going ahead, various applications in future. We now have reached the last page of the wonderful 2 days sessions. I would like to invite Shri C. Kalaivanan, Vice Chairman, AESI, Bangalore branch, to deliver vote of thanks.
Thank you, madam. We have come to the last session of vote of thanks. I'll be just sharing the screen just for a minute. Is everybody audible? Hello?
Yes, sir. Yes, sir.
Oh, then fine. 1 second. Actually, unfortunately, Mr. Khan was not available, so this responsibility was given to me because he was engaged in his own office. I take this opportunity for the International Symposium on Artificial Intelligence Machine Learning in Safety Critical System, jointly organized by INCOS, IEEE Systems Council, of course, our Aeronautical Society of India, Bangalore branch. On the first day of the inaugural function, Dr. Satish Reddy, in fact, he was very busy with the minister, especially the Ministry of Defense. He is the chief. In spite of his busy schedule, he could come to our program and talk about our topic. Maybe it is delayed. Again, I am repeating, he was busy with the ministers. in the inaugural function, Dr. Satish Reddy, then all the other 3 dignitaries were available. Then on the day one's speakers and panels, probably you can just see almost everybody from India and abroad were available for the speakers and panelists. Next, the second day also, you can just see most of them are from abroad. They have spared this time and they were helping us for this 2 days program. Thank you very much for them. The main sponsors for this program, the title sponsor Collins Aerospace, Platinum sponsor Matters and Boeing, Gold sponsor Honeywell, and Silver sponsor LDR. I thank everybody. Next, in fact, I thank Infos India IEEE Systems chapter for joining hands with AESA Bangalore Bank for organizing such a wonderful international seminar. Thanks to the sponsors. Without their support, organizing an event like this is not an easy task. With respect to the delegates, it was really a tough time to get delegates from various industries. Thanks to the delegates from industry, academia, and lab for their active participation. Very specifically, the ISRO, they were so much interested to share these 2 days with the engineers and scientists. Around 75 ISRO delegates registered, from DRDO 25, HAL 20, of course, web registration around 160. Overall registration was around 350 plus. Thanks to all the industries and academia for sponsoring these delegates for our program. And thanks to the virtual platform and digital work teams for their support. Thanks to the MCs for both days, Mrs. Aparna, Mrs. Ankita, for ensuring flow of this event in a smooth manner. Sincere thanks. In fact, their names, whatever I am going to read out, like Dr. Jepu, Dr. Ramakrishna, Mr. Prasanna, Mr. Adit, and others for their tireless contribution. In fact, they were just working. I feel it's around 11 o'clock also, they were singing to everybody. With that seriousness, we have come to this 2 days seminar. We look forward to come up with many more advanced technical events like this, sir. And all the best to everyone. Thank you very much and good night. Before everybody disperses, I request all, one and all, to listen to AESA video just for 2 seconds. Thank you very much.
From the smallest details to the highest pursuits, we are redefining aerospace. With our customers, we relentlessly tackle the toughest challenges in our industry. And every day, we imagine ways to make the skies and the spaces we touch smarter, safer, and more amazing than ever. Together, we chart new journeys and reunite families. We protect nations and save lives. And we explore the unknown. We believe in the power of intelligence and partnership to guide our customers into the future, reshaping our industry across the globe and even beyond. The paths we pave together lead to limitless possibility, and the bonds we form propel us all higher, again and again. We are constant in our evolution. We are connected to our customers, always. We are compelling as we boldly step forward. We are redefining aerospace.
In more than 75 years of our partnership with India, we have seen the nation transform and soar into the skies. It's a matter of great pride for us to have played an important role in the mission readiness and modernization of the country's defense forces, a relationship that goes back to the Second World War. A mainstay in the commercial aviation sector, we are connecting India to the world with the most fuel-efficient airplanes. It is here in India that we see the future of aerospace unfold. Innovators brimming with ideas, engineers converting imagination to reality. Leveraging this potential is an incredible opportunity, not just for India, but for the world. Building a local aerospace and defense ecosystem for an Atmanirbhar Bharat. Investing in local partnerships and nurturing homegrown talent. Committed to transforming the communities we work among and creating lasting change. We are bringing the best of Boeing to India and the best of India to Boeing.